Before humans, before cities, before history itself, the Earth turned under a different kind of night. The air was heavy and wet, rich with the scent of resin from cycads and towering conifers. In the darkness, leaves glistened with humidity, and distant shapes moved between trunks that had stood for centuries. This was the late Cretaceous, an ancient world alive with sound long after the sun had gone. From far away, a deep bellow rolled through the forest, the call of hadrosaurs gathered along a hidden river. A moment later, the ground shuddered. Not a sharp jolt, but a slow, deliberate trembling, as something colossal passed beyond the trees. A tyrannosaur. Its weight pressed footprints the size of bathtubs into the mud. Its tail swung like a fallen tree brought to life. Even unseen, its presence defined the scale of this era, a world of scale we can barely imagine. Beneath those giants, closer to the forest floor, something smaller moved. Not a lumbering titan, but a shadow among shadows. Troodon. Human-sized or smaller, feathered, light-boned, its outline broken by downy filaments that caught stray shafts of moonlight. Its head turned, and we see its eyes, huge, forward-facing, reflecting the pale disk of the moon like twin mirrors. Each step is careful. The sickle-shaped claw on its hind foot taps softly against the leaf litter, then lifts, then settles again, almost like a metronome keeping time with its heartbeat. Here in the dark, its body is modest, but its mind is not. Troodon had one of the highest brain-to-body ratios of any non-avian dinosaur, closer to modern birds and small mammals than to the massive reptiles around it. Watch how it pauses. It does not simply react, it calculates. It tilts its head, tests the wind with delicate movements of its snout, tasting the scent of hadrosaurs, of damp soil, of distant danger. It traces an invisible map between tree trunks and ferns, choosing a route that skirts the edge of the Tyrannosaur's territory, using cover, using silence. Join us as we linger on this single moment. Troodon slips to the edge of a still black pool. The stars shimmer on the surface, scattered constellations broken by ripples from an insect's wing. For a heartbeat, the little hunter is motionless, eyes flicking from sky to reflection and back again, as if studying two versions of the same universe. What thoughts pass behind those bright, alert eyes? Is this only instinct or the faint beginning of something more? Now freeze the night. The forest holds its breath. Imagine that this mind, already advanced for its time, did not end with extinction. Imagine that evolution kept pushing, generation after generation, toward ever greater intelligence. Could the first truly technological civilization on Earth have worn feathers and claws instead of skin and thumbs? As we step back hundreds of millions of years to set the stage for that possibility, we have to ask one more question. In a world ruled by the biggest creatures to ever walk the Earth, what if the future belonged to the smallest hunter in the dark? In that darkness, our small hunter finally steps into the light of science. Troodon was real. Not a myth, not a monster from fiction, but a late Cretaceous predator that lived roughly 75 million years ago in the final chapter of the Mesozoic era. It was no colossal tyrant. An adult Troodon was roughly human-sized from nose to tail, with a lightweight body, long legs, grasping hands, and a skull that housed something extraordinary for its time, a relatively massive brain. When we compare brain to body, Troodon stands out among non-avian dinosaurs. Its brain-to-body ratio approached that of modern birds and some mammals. Large forward-facing eyes suggest keen vision, perhaps in twilight or at night, and its slender jaws and serrated teeth point to a precise, selective hunter rather than a brute force killer. Fossilized nests and carefully arranged eggs hint at parental care, maybe even complex social behavior. In a world ruled by the biggest creatures to ever walk the Earth, Troodon was not the strongest, but it may have been one of the smartest. That simple fact opens a door. How far could dinosaur intelligence have gone if the story had continued? Given millions more years of evolution, could Troodon's descendants have developed language, tools, even technology? What kind of ancient world would an intelligent troodontid species shape under the shadows of giants? And in such a timeline, would mammals and eventually humans ever rise to take the stage at all? Join us as we step back hundreds of millions of years in a different way, not just to watch what happened, but to ask what might have been. This film stands in a long tradition of scientific thought experiments where researchers test the boundaries of possibility to better understand reality. In the 1980s, paleontologist Dale Russell proposed the now famous Dinosauroid, a speculative descendant of Troodon with a large brain, upright posture, and nimble hands. His model was controversial, but it asked a powerful question. If intelligence is so useful, why would it stop with us? Here, we will blend hard evidence with carefully signposted speculation. First, we will explore Troodon's biology and environment, reconstructing its senses, growth, and behavior from bones, nests, and the landscapes they were buried in. Then we will follow plausible evolutionary upgrades, changes to hands, posture, vocal organs, and brain structure that could push a clever hunter toward a thinking engineer. From there, we will imagine a troodontid civilization, tracing how cities, tools, and energy use might emerge in a world of scale we can barely imagine. Throughout this journey, scientists are our guides, digging through rock and time. Fossils, modern bird intelligence, and evolutionary theory set the boundaries of what could have been. In the next section, we begin at the ground level, with the real Troodon itself, and the late Cretaceous world it actually knew. We begin at the ground level, but before we analyze bones and brain cases, we want you to be there. Imagine yourself sitting quietly in a late Cretaceous forest, the air warm and heavy, the calls of distant giants echoing through the trees. Beside you, half hidden in ferns, a Troodon watches the same strip of sky you do. Two sets of eyes fixed on the same fading light, but processed by two very different brains. You see a sunset. It sees opportunity. Its large, forward-facing eyes drink in the dimness, tuned to crepuscular shadows. Its head, no bigger than your hand, holds one of the highest brain-to-body ratios of any non-avian dinosaur. As we step back hundreds of millions of years in our minds, you and this small predator share a moment in an ancient world, separated by an era yet bound by curiosity. Pause here with us for a pattern interrupt. Where are you watching this from right now? Which continent? Which city? Which small room lit by a single screen? Let us know in the comments where in the world you are and what time of day it is for you. Midnight in Sao Paulo. Early morning in Nairobi? Late afternoon in Toronto. By anchoring your present moment to this deep time forest, we set the stage for a journey that connects your life to a creature that vanished 66 million years ago. Because this will not be a short glimpse, this is a feature-length exploration, a documentary experience. Join us as we settle in together. Take a moment to dim the lights, choose a comfortable seat, perhaps pour a drink or a cup of tea, and allow the modern world to recede just a little. For the next 2 hours, we will walk beside Troodon through a world of scale we can barely imagine. Ahead of us are entire civilizations that never were. We will visit a troodontid city built in the shadow of colossal sauropods, delicate towers, and nesting terraces threaded between the pillar-like legs of the biggest creatures to ever walk the earth. We will look up with dinosaur astronomers, charting slow-moving points of light, tracking the path of the asteroid that will one day end their age and threaten their own extinction. We will explore an alternate Earth where mammals never take center stage, where our lineage remains small and nocturnal, while feathered reptiles shape history. Through all of this, we will move carefully between what fossils can tell us and what reasoned speculation allows. When we speak from evidence, you will know it: real nests, real teeth, real brain impressions. When we imagine Troodon tools, languages, or energy use, we will say so clearly. Along the way, you will learn real paleontology and evolutionary biology, even as we follow this thought experiment to its furthest edge. In the next section, we return to that forest and meet the real Troodon in detail. The forest fades. For a heartbeat, the sounds of insects and rustling leaves fall away, replaced by the low roll of distant drums and a single, echoing call from something unseen. We rise above the canopy, above the late Cretaceous shoreline, until the coast itself becomes a sweeping arc of surf and mist beneath us. This is still an ancient world, but the view is about to change. The blue of shallow seas and the dark green of conifer forests dissolve, line by glowing line, into a schematic. Cliffs become terraces, tree crowns resolve into spirals of light. Before your eyes, the wild coastline is redrawn as a troodontid city, built into stone and woven through living forest. Ramps cling to precipices where once only ferns grew. Bridges stretch from trunk to trunk like colossal spider webs of light. In this imagined design, we see streets, platforms, and towers sized not for the biggest creatures to ever walk the earth, but for quick, feathered forms with grasping hands and keen eyes. A brief music sting swells beneath us. Cinematic percussion beats like a slow, deliberate heart, while distant animal calls echo from the darkness at the edge of the frame. It feels both grand and uncertain, as if we stand on the threshold of a world of scale we can barely imagine, not in body size, but in thought. What does intelligence look like when it evolves under the shadows of giants? As the rhythm settles, the schematic city rotates and draws inward. Feathers of light sweep across the screen, scattering into points that curve and settle into constellations. Between them, simple icons appear and fade: a chipped stone edge, a stylized eye, a three-fingered hand. These motifs hang against a deep star-filled sky as the title resolves in the center of the frame. What if Troodon had evolved human-level intelligence? We hold there. The music thins to a quiet shimmer. For a moment, there is no narration at all, only the slow drift of star fields and the faint outline of feathered shapes crossing them. This pause lets us reset, to step back hundreds of millions of years in our minds and consider the premise not as fantasy, but as a question about evolution, extinction, and possibility on Earth. The stars dim. The title fades. In their place, a single fossil skull emerges from black, lit from one side so that every curve of bone and hollow of the eye socket stands out in sharp relief. We begin a slow, unhurried zoom toward it. The imagined city is gone. Only rock remains. Now the narration returns, quieter, more focused. We have seen the dream. Next, we ground it. Join us as we trace this skull back to the late Cretaceous, meet the real Troodon, and set the stage for how a small, sharp-eyed predator became the prime candidate for a dinosaur mind that might one day rival our own. To follow that skull back in time, we have to leave our cities, our species, and our era behind. We step back hundreds of millions of years in an instant, until the familiar shapes of continents blur and reform into an ancient world. It is the late Cretaceous, roughly 75 to 66 million years ago. North America is no single solid block, but a divided land. A warm, shallow sea, the Western Interior Seaway, stretches from the Arctic to the Gulf of Mexico, flooding the heart of the continent. To the west, a long rising chain of mountains sheds sediment into broad, lush floodplains. To the east, low coastal plains and swamps fringe this inland ocean. Here, between water and highlands, Troodon lives. The climate is a greenhouse. Global temperatures are higher than today, and there are no polar ice caps. Sea levels rise, drowning continental interiors and creating a patchwork of deltas, coastal marshes, conifer forests, and fern-filled understories. Flowering plants are spreading, adding new colors, scents, and fruits to the landscape. These conditions set the stage for diverse habitats, from misty upland forests to open river margins, where herds pass like living tides. In this world of scale we can barely imagine, Troodon is not a giant. It stands about as tall as your waist, lightly built, with a long tail for balance and a sickle-shaped claw on each hind foot. Around it move the true giants, hadrosaurs, the duck-billed herbivores whose herds thunder across floodplains, ceratopsians, horned dinosaurs with massive frills that rise like living shields above the ferns. Overhead, pterosaurs with wingspans of small planes ride the warm air above the seaway. At the top of the food web, tyrannosaurids rule. These colossal predators, with skulls longer than a person is tall, stalk the same valleys where Troodon hunts. Beneath the ferns and in the leaf litter, small mammals scurry, mostly nocturnal, exploiting seeds, insects, and burrows. Troodon moves between these scales, neither the biggest creature to ever walk the earth, nor the smallest, threading its life through the spaces the giants leave behind. Environmental pressures here are relentless. Dense forests break sightlines and force sharp memory of paths and hiding places. Day-night cycles bring different hunters and different risks. Troodon's large, forward-facing eyes hint at twilight or nocturnal activity when shadows stretch and depth perception can mean survival. Seasons shift water levels, food supplies, and migration routes, demanding flexible behavior rather than rigid instinct. Everywhere there is a complex web of predators and prey, nests and raiders, parents and offspring. Fossil nests suggest careful egg arrangement and possible parental care, adding social nuance to this sharp-toothed hunter. In such a world, what is the advantage of a slightly quicker mind, a more refined sense, a memory that reaches a little farther back in time? Join us as we hold that question. In this rich, competitive landscape, what evolutionary paths are open to a small, clever predator with unusually advanced senses? And how far could those paths lead if extinction did not cut them short? To follow that question, we need to meet the dinosaur at its center. Before we imagine cities of reptilian thinkers or tools held in clawed hands, we must step back hundreds of millions of years and stand beside the real animal. Troodon, the so-called genius of the late Cretaceous. At first glance, Troodon would not dominate your field of view the way the biggest creatures to ever walk the earth once did. Fully extended, it reached roughly human height, but it was lightly built, far closer to a lanky runner than a massive bruiser. A long, stiffened tail stretched out behind it like a balancing pole, counterweighting a narrow feathered body and a slender, flexible neck. Each foot carried a distinctive weapon, an enlarged, sickle-shaped claw on the second toe, held off the ground and ready to rake downward into struggling prey. This was no lumbering brute. Its limbs were built for speed and agility, its tail for balance, its feathers for insulation and display in a changing, dynamic world. When you picture Troodon weaving between tree trunks or darting across a moonlit floodplain, you begin to see the kind of predator that might benefit from planning, memory, and split-second decisions. Look closer at the head, and the case for unusual intelligence deepens. Troodon's skull was relatively short and lightly built, with a beak-like snout lined by small serrated teeth. Those teeth were not the heavy blades of a tyrannosaur. Instead, they suggest an omnivorous or small prey diet, capable of handling insects, small vertebrates, and perhaps plant material. Above the jaws, two enormous forward-facing eyes dominated the face. Their size and orientation hint at excellent binocular vision. The precise, depth perception you need to snatch quick, elusive targets. Some researchers have even proposed that Troodon may have been nocturnal or crepuscular, using those large eyes to hunt at dawn, dusk, or in near darkness. What kinds of challenges does such a lifestyle impose on a brain? Inside the skull, the story becomes even more striking. Endocasts of troodontid brain cases show a brain-to-body ratio among the highest known for non-avian dinosaurs, edging into the range of modern birds and small mammals. Join us as we consider what that means. Relative to its size, Troodon carried far more neural tissue than a typical reptile of its era. Enlarged regions associated with vision and balance, and a proportionally big forebrain, mark troodontids as cognitive outliers, the mental sprinters in a landscape of muscle-driven hunters and colossal herbivores. The fossils do not end with bones and brains. In sediments that once formed nesting grounds, paleontologists have uncovered troodontid eggs arranged in careful rings, some with adults preserved close by. These circular nests, the paired eggs, and the posture of brooding individuals suggest parental care, perhaps even prolonged guarding and turning of the clutch. Such behavior requires more than reflex. It hints at social interaction, learning, and communication. Could these family groups, bound by care and memory, have set the stage for richer social structures over millions of years? Troodon was not an isolated experiment. It sat on a branch of the dinosaur family tree that ultimately leads to modern birds. When we watch crows solving multi-step puzzles or parrots using tools today, we are seeing the cognitive ceiling that dinosaur brains can reach. In Troodon, we glimpse an ancient starting point. In the next section, we will ask how far that starting point might have climbed if extinction had not intervened. To understand how far that starting point might have climbed, we need to ask a deeper question. How smart can a dinosaur realistically become? Not in myths or monsters, but in the slow, methodical language of evolution, written into tissue and bone. One of the simplest tools we have for comparing minds across the tree of life is the encephalization quotient, or EQ. EQ looks at brain size relative to body mass and asks whether an animal carries more brain than we would predict for its weight. It is not a perfect measure, but it offers a rough proxy for cognitive potential across species, a way to compare an ancient predator with a modern crow or primate. When we place Troodon on this scale, something remarkable happens. Its estimated EQ rises well above that of typical reptiles, edging into the range of modern birds and some mammals. In an era dominated by muscle and teeth, Troodon carried a brain that was disproportionately large, with forward-facing eyes and dense sensory regions. It was not human level, not even close, but for its time it was a standout, a neurological outlier on a Cretaceous landscape filled with giants. Yet raw size is only part of the story. Brain structure matters just as much as volume. Mammals like us rely on a layered neocortex, a sheet of tissue responsible for flexible problem-solving, planning, and language. Reptilian and early dinosaur brains were organized differently, with more emphasis on structures like the dorsal ventricular ridge and basal ganglia. As some dinosaurs evolved into birds, these regions expanded and reorganized, producing a compact, highly efficient avian brain. Different architecture, same goal: to process information about a complex world. Modern corvids and parrots show us what this alternate design can do. Their brains are small by volume, yet highly folded and densely packed with neurons. Crows can solve multi-step puzzles, remember human faces, and plan for future rewards. Parrots can use tools, learn vocal symbols, and share skills through social learning. Join us as we consider that these birds are, in a sense, living experiments in what a dinosaur-style brain can achieve without a mammalian neocortex. If Troodon already sat near this avian frontier in EQ, we can ask a provocative question. Given millions more years, could a lineage starting from that baseline refine its circuitry, pack in more neurons, and cross the threshold into truly technological intelligence. The Mesozoic era offers a world of scale we can barely imagine, but its neurological rules were the same as ours. Selection favors whatever minds solve problems best. In the next section, we will step back hundreds of millions of years and then move forward along an alternate timeline, tracing how those rules might have reshaped Troodon's body, senses, and society. What would it take for a small, bright-eyed predator to rival the biggest creatures to ever walk the Earth not in size, but in thought? To imagine Troodon thinking like us, we first have to disrupt something deep in our minds. When most of us picture intelligence, we see a big, rounded head, upright posture, and hands shaped almost exactly like our own. We are quietly tracing the outline of a human. For more than a century, science fiction has reinforced that picture. Again and again, alien giants of the cosmos arrive as tall, two-legged figures with smooth faces, expressive eyes, and delicate fingers. Not just visitors, but reflections. Different skin, different world, same basic body. But what if that image is not a law of evolution, only a habit of thought? What if a world of scale we can barely imagine could host minds in shapes we barely recognize? Here is the pattern interrupt. Intelligence is not a skull shape. Intelligence is problem-solving software that can run on many kinds of biological hardware. Corvids, with their sleek wings and sharp beaks, can plan several steps ahead to access food. Octopuses, with no bones at all, explore, test, and manipulate using 8 arms packed with nerves, each arm partially thinking for itself. Parrots, dolphins, and apes all reached impressive cognition along different anatomical paths, constrained by their bodies, yet empowered by them. Join us as we look again at Troodon through this wider lens. In the 1980s, paleontologist Dale Russell proposed the famous Dinosauroid, a hypothetical descendant of Troodon that survived the Cretaceous extinction and evolved human-level intelligence. His model stood upright, lost its tail, had a rounded skull, a flat face, and flexible hands remarkably similar to ours. It was a striking image, and it captured public imagination. Yet many modern paleontologists now see it as misleading, not because intelligence in dinosaurs is impossible, but because the model simply turned Troodon into a reptilian person. Why should an intelligent dinosaur abandon the very design that made it successful? Troodontids were light, horizontal-bodied predators with long balancing tails, feathers for insulation and display, and lethal sickle claws on their feet. Their eyes already faced forward for depth perception. Their brain-to-body ratio was among the highest of their era. Evolution does not need to erase that legacy to build a better mind. An advanced troodontid might still run low to the ground, tail streaming behind like a living counterweight. Feathers could thicken into expressive crests and facial fans, broadcasting emotion and status. The sickle claw, once used to pin struggling prey, might become a precise climbing tool or a way to anchor delicate work. Hands could refine, wrists could rotate further, but the overall silhouette would remain unmistakably dinosaurian, not a thinly disguised human. In the next part of our journey, we will set the stage for this alternative body plan in detail. We will redesign Troodon's hands, posture, and senses, not by forcing them toward our image, but by asking a different question. How do you maximize what a dinosaur body already does well? As we step back hundreds of millions of years and then move forward along this alternate path, what kind of civilization might grow from that form? To understand how a thinking troodontid might arise, we have to slow our imagination down to evolution's pace, not years, not centuries, tens of millions of years, across an era of shifting continents, changing climates, and repeated brushes with extinction. Human-level intelligence is not a quick upgrade. It is a rare outcome that demands a stable niche, relentless selection pressures, and a long stretch of geological time in which being clever consistently pays off. Before we picture cities of feathered reptiles, we must first ask, what kind of ancient world would reward a small predator for becoming a problem solver, rather than simply a faster runner or a stronger biter? Join us as we follow one hypothetical troodontid lineage that survives the late Cretaceous in scattered refugia. Imagine cooler upland forests, coastal swamps, and island chains where the colossal open plain giants are fewer and the environment is more unpredictable. In these pockets, storms, fires, and shifting food sources repeatedly disrupt the old rules. Here, a slightly better memory, a touch more curiosity, or a more flexible hunting strategy can mean the difference between leaving eggs in the nest or vanishing from the fossil record. Over generation after generation, subtle mechanisms begin to set the stage for something extraordinary. Neoteny, the retention of juvenile traits into adulthood, keeps brains proportionally large and behavior more exploratory. Social complexity deepens as these nimble predators experiment with cooperative hunting, surrounding hadrosaurs in shadowed forests, or flushing small mammals from burrows together. Selection favors individuals that can read allies' intentions, negotiate hierarchies, and remember who shared food and who cheated. In parallel, environmental instability selects for behavioral flexibility. Some troodontids learn to cache food, to probe rotting logs, to raid nests that are hidden rather than exposed. A slightly more opposable second finger, a wrist that rotates a few degrees farther, turns a simple grasp into the beginnings of manipulation. Not hands like ours, but hands precise enough to roll stones, tear fibers, and probe crevices with sticks. Each step is small, a marginally sharper working memory, a more nuanced repertoire of calls that shades from simple alarm cries into graded signals about predators, food, or individuals. Parents that stay a little longer, tutoring juveniles in local dangers and opportunities. Over millions of years, these increments accumulate until the qualitative boundary begins to blur. We are no longer looking at just another clever dinosaur. We are watching minds that plan seasons ahead, invent new foraging techniques, and perhaps reshape their surroundings. All of this unfolds under the slow ticking of a cosmic clock. Because far above this evolving lineage, a future asteroid is already on its silent path. When the KPG impact finally tears into the crust and plunges Earth into darkness, will these upgraded troodontid descendants simply be one more casualty of a global catastrophe? Or will their hard-won intelligence offer them a way to adapt where so many giants fall? If intelligence gives our hypothetical troodontids a chance to outthink extinction, their survival will still come down to something far more tangible: what those clever brains can actually hold. Before we imagine cities or starships, we have to look at hands, claws, and the very first stick picked up from the forest floor. In the real late Cretaceous world, Troodon already carried an impressive toolkit on the ends of its arms. Each forelimb bore 3 functional fingers, tipped with curved claws and backed by strong tendons. The inner digit could fold toward the others in a semi-opposable grip, allowing the animal to seize struggling prey, clutch branches, or pull at carcasses with a precision many other theropods lacked. These were not the stiff, hook-like hands of a colossal tyrannosaur. They were lighter, more flexible, already edging toward manipulation rather than pure restraint. To understand how far such a lineage could go, we can look at modern birds. Parrots, for example, do not have mammal-style hands at all, yet they crack seeds, strip bark, and even use sticks by combining beak and zygodactyl feet as multi-purpose manipulators. Crows and ravens, descendants of other ancient theropod lines, probe with their beaks, brace objects with their toes, and solve multi-step puzzles that rival primates. Join us as we use these living relatives to set the stage for what a refined troodontid grip might achieve. Over millions of years of evolution, Relatively modest anatomical tweaks could transform those three-fingered hands into true instruments of technology. Increased finger independence would allow each digit to move on its own, rather than as a mostly unified clamp. Extra joints and more flexible wrist bones could rotate and angle tools into just the right position. Strengthened and more finely divided tendons would give both crushing power and delicate control, so a future troodontid could still pin prey, yet also weave plant fibers or chip flakes from stone without shattering them. But every upgrade carries a cost. How much of the original hunting arsenal could be preserved? The famous sickle claw on the second toe, used for slashing or gripping, might become even more important as the forelimbs shift toward manipulation, keeping the hind limbs as primary weapons while the arms specialize. The jaws and teeth could share the load as well, holding objects steady while the hands work, much as parrots brace food with their beaks. In this way, predatory function is not abandoned, it is redistributed. Imagine then an intelligent troodontid at the edge of a Cretaceous river, its semi-opposable fingers now fully articulate. It selects a straight twig, strips it with a few precise bites, and uses it to probe for hidden prey in the mud. Nearby, others arrange stones as simple anvils or twist flexible stems into crude chords. These are humble tools, yet they set the stage for a world of scale we can barely imagine, where repeated use and cultural learning turn sticks into spears, woven fibers into nets, and carefully chosen rocks into the first cutting blades. What happens when such behavior collides with fire, shelter, and eventually complex social planning? In the next step of this alternate timeline, we will follow those hands away from the forest edge and into the heart of troodontid society itself, where cooperation, communication, and shared knowledge begin to reshape the ancient Earth. Those hands do not exist in a vacuum. Every tool, every shared task must be anchored in a body that can move, balance, and work in a demanding ancient world. When we imagine an intelligent troodontid, we are not just changing the skull, we are rewriting the entire posture of a predator shaped by the late Cretaceous. To see where evolution might take it, we first need to see where it began. Troodon, as we know it from the fossil record, carried its torso almost horizontal, with a long feathered tail stretched out behind like a living counterweight. It walked on its toes in a digitigrade stance, legs underneath the body, feet narrow and precise. This was a creature built for quick dashes and sudden pivots, more like a ground-running bird than the lumbering giants that often dominate our image of the Mesozoic era. Its balance was already a masterpiece of biomechanics. Now imagine that same frame asked to think, plan, and manipulate. Does the torso rise? The spine tilting closer to vertical to free the arms for longer periods of work? A more upright posture would make it far easier to hold tools at chest height, to inspect objects with those large forward-facing eyes, and to interact face-to-face with other members of its group. It would begin to set the stage for long sessions of crafting, building, and teaching. Yet, there is a cost. Raising the body high would lift the center of mass, reduce stability during rapid turns, and expose more surface area to predators and rivals in a world still filled with colossal theropods. Instead of leaping straight to a humanoid silhouette, evolution could favor intermediate solutions. Picture an intelligent troodontid that remains mostly horizontal while moving, but can partially elevate its torso when stationary, hips flexing, tail dropping to form a third point of support. In that tripod-like stance, the animal could brace itself while carving wood, chipping stone, or weaving plant fibers. It might regularly rear up against trees, rock faces, or even the flanks of dead giants to work at different heights, using the environment itself as a temporary workbench. The familiar hunting posture would still dominate during travel and pursuit, but moments of concentrated labor would look very different. For this flexibility to succeed, balanced systems would need to refine rather than reinvent themselves. The inner ear canals, which help modern birds and reptiles sense head orientation, could become even more sensitive to rapid shifts between low running postures and raised semi-erect stances. Tail musculature might strengthen and diversify, allowing subtle adjustments that keep the center of gravity aligned over the feet as the torso rises and falls. Join us as we consider how such changes, accumulated over millions of years of evolution, could allow fluid transitions between locomotion modes without sacrificing the agility that once meant survival. The result is an intelligent dinosaur body that feels strikingly alien to us. Neither fully upright nor locked in a permanent crouch, this troodontid would move through a world of scale we can barely imagine, flowing from horizontal sprint to braced, tool-using stance as tasks demand. As we step back hundreds of millions of years in our minds, we can ask, how would such a creature build, hunt, and travel across landscapes still ruled by the biggest creatures to ever walk the earth? In the next section, we will follow that shifting posture outward into trails, shelters, and the first true troodontid-built spaces on this changing planet. From shifting limbs and tools, we now move to something even more elusive, a voice. Not just a hiss or a screech, but patterned sound that could carry meaning through the ancient dark. In modern birds, that power begins in a remarkable organ, the syrinx. Unlike our single human voice box high in the throat, the syrinx sits deep in the chest where the windpipe splits, and it can control separate streams of air at once. Songbirds weave intricate melodies, parrots mimic human speech, and some can whistle entire tunes with uncanny precision. Join us as we ask, did troodontids, distant cousins within the same great dinosaur family tree, possess the first rough outlines of such a system? We do not have a fossilized syrinx from Troodon itself, but the discovery of a syrinx in a late Cretaceous bird suggests the basic blueprint was already emerging before the end of the Mesozoic era. Over millions of years of evolution beyond that point, an intelligent troodontid lineage could refine this early apparatus, turning simple calls into a flexible tool for communication. The path would run through bone, muscle, and brain. To speak in anything like language, their skulls and throats would need to change. The hyoid bones, which support the tongue and throat in many vertebrates, might lengthen and branch, anchoring stronger muscles for fine control of clicks, trills, and sustained notes. The airway could widen or gain subtle valves, allowing rapid shifts in pitch and volume. Deeper in the chest, more refined respiratory control, long, steady exhalations rather than short bursts, would support extended strings of sound, the first sentences of a non-human world. Inside the brain, new neural circuits for vocal learning would have to bloom. In parrots, songbirds, and corvids, specialized clusters of neurons allow individuals to memorize sounds, practice them, and recombine them in novel ways. These modern avian giants of cognition solve puzzles, recognize faces, and even invent local dialects. Their abilities show that dinosaur-descended brains are already capable of sophisticated vocal behavior. A troodontid brain with an even higher investment in planning and social awareness could push this further, turning calls into structured, learned patterns, true proto-language. Now imagine the acoustic environment that would shape those patterns. Dense Cretaceous forests, layered with ferns and conifers, would muffle high, thin sounds, but carry low hoots and sharp clicks between trunks. Background choruses of insect buzz, distant hadrosaur bellows, and the occasional colossal roar from the biggest creatures to ever walk the earth would crowd the soundscape. Many troodontids were likely nocturnal or crepuscular. In that dim period between day and night, clear communication would be precious. Short, contrast-rich syllables, paired notes, and rhythmic sequences might evolve because they cut through leaves, fog, and the calls of other dinosaurs. In such a world of scale we can barely imagine, what would an intelligent predator omnivore choose to name first? Prey animals and their habits, safe paths and dangerous clearings, or perhaps recurring lights in the sky that marked seasons and migrations. As we set the stage for their emerging culture, we now have to ask, if a troodontid voice could speak of more than survival, what stories would it tell next? To glimpse what those stories might sound like, we need to leave theory behind for a moment and walk beside them. Join us as we step back hundreds of millions of years into the last light of a late Cretaceous afternoon and follow a single clan of slightly more advanced troodontids through one full, fragile day. Before names, before written history, there is a pattern. A shared nest hollow at the forest edge, ringed with stones deliberately dragged into place, feathers and leaves woven into a low, insulating wall. Adults stir first, not in chaos, but in a quiet sequence. 2 slip away toward the river margin. 3 move to higher ground to scan. 1 remains among the juveniles, her posture and soft clicks holding the group together. This is not just a pack. It is the faint outline of roles. They hunt as a loose net, not just chasing, but steering. One troodontid circles wide, flashing pale feathers to flush small mammals from the undergrowth. Another waits motionless, sickle claw poised, while a third trots along a fallen log, testing the air with careful, deliberate head tilts. When a nest of ground-dwelling birds is found, the strategy changes again. A thin branch is wedged under a flat stone, forelimbs and body weight pressing down. The stone lifts. Eggs roll free. Juveniles watch every motion. One mimics the levering action, but clumsily, sending the branch skittering away. An elder snaps a sharp, descending call, then repeats the movement slowly, exaggerating limb angles, tail held stiff for balance. The youngster tries again. This time, success. The reward is not only food, but a low, rhythmic coo from the adult, a sound that in this world means approval. As the sun climbs, tool use becomes part of the landscape. A narrow stick is probed into a crevice, then pulled out speckled with insect bodies. Bits of meat are cached high in a tree hollow, carefully pushed deep with the same stick and marked with a scrape on the bark. Do they remember which mark is theirs? The juveniles follow, tracing the grooves with their snouts, murmuring soft contact calls as if reciting a mental map. Night falls and the forest changes. Many giants sleep, but these smaller hunters remain active. Around a familiar bleached tree stump that rises like a pale pillar, the clan gathers. Bodies touch, feathers brush. They trade sequences of whistles, clicks, and posture displays that rise and fall in repeating patterns. One adult reenacts the day's successful hunt in pantomime, head jerks and tail sweeps, matching specific calls. Others answer with echoing phrases as if adding verses to a shared memory. Are we watching the first shadows of ritual, or simply complex coordination? In this ancient world, the line is thin, and yet, everything we have imagined here is anchored in real behavior we see today in crows, parrots, and mammals, such as meerkats and chimpanzees. As we return from this vignette to the broader sweep of evolution, we can now ask with sharper focus, if such protoculture was possible, what anatomical changes would let troodontids push it into true civilization? In this imagined Cretaceous future, intelligence does not evolve in isolation. It evolves in company. Before written laws, before cities, before any notion of civilization, there is the tribe, the hunting band, the watchful circle of eyes and minds. This is where troodontid intellect would be forged. Biologists call it the social brain hypothesis. The idea is simple but profound. In many animals, the greatest mental challenge is not the landscape or the prey, but other members of the group. To survive, you must track who helped you, who betrayed you, who leads, who follows, and who is quietly waiting for a chance to rise. Join us as we step back hundreds of millions of years and imagine troodontids facing exactly these pressures, their brains expanding not just for hunting, but for understanding one another. What might their groups look like? We can picture small hunting bands, 5 to 10 individuals ghosting between tree trunks, using soft calls and subtle gestures to coordinate. Around rich nesting grounds or seasonal carcass sites, those bands might fuse into larger colonies, temporary towns of feathered bodies and flicking tails. In safer regions, extended family units could persist for years, with multiple generations sharing territories, much as wolf packs and meerkat clans do in our own world. Each structure sets the stage for different cognitive demands. Coordinated ambushes require planning and role assignments, some troodontids driving prey, others waiting in the shadows, holding position until a signal flashes through the undergrowth. Shared childcare means remembering which chick belongs to which parent, and tolerating non-parents that help guard and feed the young, as we see in cooperative birds. Food sharing demands restraint, negotiation, and the ability to weigh present hunger against future allies. From this constant negotiation, social rules would emerge. Cheaters who take food but never help hunt might be bitten, excluded, or pushed to the edge of the group. Dominant individuals would establish status hierarchies, but their power would depend on reputation. Too much aggression, and subordinates might quietly form alliances against them. After fights, reconciliation behaviors, gentle touches, soft vocalizations, careful grooming of feathers could repair bonds, just as they do in primates and ravens. To navigate such a world, a troodontid needs memory, impulse control, and something like a theory of mind. The ability to guess what another is about to do. Once these dinosaurs can track reputations, anticipate reactions, and plan several moves ahead socially, a deeper question appears. How long before their planning stretches not just across days or seasons, but across generations? When elders remember old nesting grounds, when hunting strategies are taught and refined, when stories of past droughts or predators are repeated through ritualized displays, the foundations of culture and tradition begin to solidify. In a world of scale we can barely imagine, among some of the biggest creatures to ever walk the earth, troodontids could become the quiet strategists, weaving invisible networks of obligation and memory. And if their minds reach that point, what anatomical changes would allow them to carry those traditions into tools, symbols, and, eventually, true civilization? Those traditions need somewhere to live, not just in bodies and behaviors, but in minds that can stretch across time. When we talk about a truly intelligent troodontid, we are talking about a brain that can perform what neuroscientists call episodic memory and mental time travel. Episodic memory is the ability to replay specific past events, a certain clearing, a particular night, the exact scent of a predator on the wind. Mental time travel builds on this, allowing an animal not only to revisit those moments, but to project itself into possible futures. Without this, there can be no genuine long-term planning, only instinct and habit. We see the beginnings of this in our own era, in creatures far smaller than the biggest creatures to ever walk the earth. Corvids, crows, ravens, and jays, cache food in dozens or even hundreds of hidden sites, then return weeks or months later to recover it. Experiments show that they remember not only where they stored food, but what they stored and how long ago, choosing to retrieve items before they spoil. They can even re-hide caches if they realize another bird was watching. That is primitive mental time travel in action. Now step back hundreds of millions of years in your imagination and place that style of thinking inside a troodontid. This late Cretaceous genius dinosaur already has a large brain for its size, keen vision, and a flexible predatory lifestyle. Selection pressures in its ancient world would constantly reward those individuals that could look beyond the next hour. Seasonal resource scarcity would favor troodontids that remember which valleys held nesting herbivores last year, and which riverbanks grew seed-bearing plants after the floods. Migration routes of prey herds, the timing of pterosaur nesting on distant cliffs, even the periodic movements of larger predators would all become patterns to store compare, and project forward. Over thousands of generations, troodontids that can plan not just days but months and eventually years ahead gain a decisive edge. A lineage that anticipates the return of drought, that times its own breeding to peaks of food abundance, that shifts hunting grounds before competition arrives, will leave more descendants. Mental time travel becomes a survival tool, then a social tool, and finally, the quiet engine driving a technological trajectory. At that point, another transformation becomes possible. Symbolic thinking. Once a troodontid can imagine absent events, it can begin to use marks, sounds, or objects to stand for those absences. A scratched spiral on bark might mean nesting site to the north. A specific sequence of calls at dusk might signal danger returns with the cold rains. Arranged pebbles near a communal path could encode how many days remain until a herd usually returns. These are not yet full writing systems or formal mathematics, but they set the stage for both. Because the moment a species can imagine futures and then anchor those futures outside the brain, in carved lines, in notched bones, in deliberate patterns of stones, history, in a real sense, can begin. And if troodontids ever reach that threshold, the next question becomes inescapable. What kinds of bodies and tools would they reshape to turn those fragile symbols into enduring machines of knowledge? To answer that, we have to ask something deceptively simple. When do scratches in the dirt stop being damage and start being information? When does a mark on a surface begin to stand in for a thought? Once troodontids cross that invisible line, they are not just clever hunters in an ancient forest. They are authors. We step back hundreds of millions of years into a late Cretaceous night where the biggest creatures to ever walk the earth sleep in the distance, and smaller, sharper minds move in the shadows. A troodontid patrols a ridge, dragging its claw along a tree trunk. At first, this is just territorial behavior, like a cat's scratch or a bird's drum. But imagine those scratches placed in the same pattern at the same bend in the river, generation after generation. The mark becomes a message. Here is our boundary. Here is the safe path. Here is where the giants pass. Early symbolic behavior would not look like neat rows of characters. It would look like habit. Feathers deliberately arranged at a nest entrance in a consistent pattern. Pebbles stacked in a narrow canyon where predators lurk. A particular call only ever given near a fertile nesting ground. Each action ties a sound or shape to a place, a danger, a resource. Over time, those associations can solidify into a primitive code that every youngster must learn. From there, proto-writing can emerge almost quietly. Join us as we follow a troodontid clan along its migration route. At key junctions, elders gouge repeated claw marks into bark or soft stone, not at random, but in ordered clusters. 3 deep slashes for the long way around the swamp, 1 angled cut for the steep but fast ridge path. On fallen logs near nesting sites, they notch tally-like grooves, 1 for each clutch of eggs, or each large prey animal brought down that season. These are not stories yet. They are accounts. Human writing began the same way. Long before literature, clay tokens, cuneiform tallies, and knotted cords recorded grain, debts, and herds. The first archives were not libraries of myths, but ledgers. In a similar way, troodontid script might first crystallize around counting prey, tracking eggs, and mapping safe corridors through a world dominated by colossal herbivores and massive predators. The Mesozoic world offers many potential pages: bark that can be peeled and incised, clay-rich mud pressed and dried in the sun, soft limestone cliff faces that yield to repeated pecks of a beak and rakes of a claw. Even shells and bones, drilled and scored, could carry portable records. Their anatomy is ready-made for this task. Narrow claws for fine incisions, beaks for chipping and smoothing, agile necks to work close to a surface. Once information lives outside individual brains, cultural evolution can surge. A route remembered by one hunter becomes a map used by dozens. A clever hunting strategy, scratched into stone, survives the extinction of its inventor. Over thousands of years, symbols for numbers and places might bloom into marks for sounds and ideas, setting the stage for true writing. And when a species can read its own past directly from the landscape, what new futures does it begin to imagine next? Those imagined maps and symbols do not float in the air. They are carved, knapped, and tied into the very objects troodontids hold in their claws. Before there is writing, there is work. And work demands tools. In this ancient world, before metals, before engines, a troodontid stone age would begin with the simplest categories: sharp cutting edges for slicing flesh and plant fibers, heavy pounding stones for cracking bone and seeds, digging implements for prying roots and burrowing prey from the soil, and crude bindings or containers woven from leaves and sinew. Not just possessions, but extensions of the body. Each new shape of rock or bone would widen the range of problems they could solve. Anatomy would guide every design choice. These are not primates with flat hands and thumbs. They are feathered predators with sickle claws, grasping three-fingered hands, a narrow beak, and a long, flexible neck. Instead of straight wooden handles built for a human fist, we might see hooked, clampable forms that lock neatly against a curved talon, or crescent-shaped grips that can be pinched between claw and palm, while the neck angles the head for precision. A beak can nip, hold, and twist, so small blades might be socketed into ridged bone or wood, turning the entire skull-neck system into a delicate cutting arm. The technological sequence would likely mirror our own in broad strokes, yet diverge in its details. It begins with opportunistic use of naturally sharp rocks, picked up beside rivers or volcanic outcrops when a carcass proves too tough for teeth alone. Over generations, those lucky finds become deliberate choices. Certain stones are favored, certain fracture patterns remembered. Join us as we imagine the first intentional flake struck from a core. The first time a troodontid realizes that shape is not found, but made. From there, composite tools follow. A chipped stone tip, wedged into a hollow bird-like bone and lashed with plant fibers, becomes a light spear that can be held in the forelimbs while the feet remain free to slash and grip. Digging claws are augmented with antler-like prongs or sharpened ribs to open burrows faster. Knives, scrapers, wedges, and hammers accumulate into a true toolkit, setting the stage for cultural traditions of craftsmanship passed from nest to nest. Their environment would invite innovations we never needed. Giant conifers tower over the forest. Specialized climbing hooks of bone and wood could help troodontids swarm up trunks to raid eggs from arboreal nests or reach nutritious cones. Carefully shaped spikes might breach the leathery shells of massive dinosaur eggs, while heavier, chisel-tipped clubs focus force on the plated hides of ankylosaurs, turning impenetrable armor into a challenge rather than a barrier. Hollowed bones plugged with resin become containers for rendered fat or collected seeds. Sharpened sticks and stone-tipped awls open pathways to sticky veins of tree sap that can be eaten, burned, or used as glue. All of this unfolds on a volcanic, mineral-rich earth, where obsidian glitters beside steaming vents and strange clays bake hard in natural fires. Do these troodontids remain in a long stone and bone Paleolithic, perfecting ever finer flakes and bindings? Or does some curious mind notice that certain stones melt and flow near lava, that certain pigments fuse into something new, and step across a threshold far more transformative than the first sharp edge? If a dinosaur civilization reaches that point, are we still talking about a simple Stone Age at all? Or the first sparks of an entirely different technological era? So let us step back hundreds of millions of years, away from talk of metals and melting stone, and stand instead beside a quiet Cretaceous river at dusk. The air is heavy and warm. The sky is fading from gold to deep violet. Here, the first faint outlines of a troodontid culture are taking shape. Along a gentle bend in the river, the forest edge opens into a narrow clearing. This is not a random gap in the trees. The ground has been deliberately scraped of loose branches and sharp stones, leaving a smooth, trampled surface patterned with three-toed tracks. Above, several low branches bear the same pale scars, where bark has been stripped away again and again. These are repeated sleeping perches, reused night after night, a semi-permanent camp in an ancient world that rarely pauses. Around the clearing, a loose ring of trees stands marked. Claw-gouged spirals climb their trunks. Patches of bark have been stained with crushed pigments from iron-rich mud and ground berries. This is territory claimed, signaled, and remembered. It is not a city, not yet, but it is more than a simple resting spot. It is a place that holds meaning. Within this circle, troodontids move with quick, precise intent. One adult crouches near a flat river stone, turning a shard of chert between delicate half-feathered hands. There is a rhythmic tapping of claw on stone, then a sharper crack as a flake shears away. Not a single blow, but a practiced sequence, each strike adjusting the edge, refining the curve. Nearby, another individual sorts through a small scatter of tools, placing longer blades together, shorter scrapers in a separate cluster. The smell of crushed ferns drifts through the camp, released under careful feet as others strip leaves and stems from gathered plants. Small prey carcasses hang from low branches, their skin opened with astonishing precision. Flesh is sliced into narrow strips and laid across warm rocks, where the last heat of the day slowly dries them. We are watching food preparation, not mere feeding. At the edge of the clearing, two juveniles test themselves against a tangle of fallen trunks. An elder weaves through the maze first, demonstrating a winding path, then retreats and watches. The young troodontids hesitate, then follow, learning to judge distance, balance, and the shifting groove of decaying wood. This is teaching through example, skill passed from one mind to another. As the light fades, a pattern interrupt cuts through the ordinary. One troodontid climbs onto a prominent rock at the center of the clearing and freezes, head raised. Others turn toward it. For a long moment, nothing moves. Then a low pulsed call rises from the leader's throat, joined in staggered unison by the rest. Feathers along arms and tails flare and settle in slow waves, catching the last traces of light. Are they reinforcing bonds, mapping the day and sound, or reaching for something beyond immediate survival? Join us as we pull back, lifting above the treetops. Beyond the fragile ring of marked trunks, colossal shapes move through the dusk. A line of sauropods, the biggest creatures to ever walk the earth, drifts past like living hills, their necks sweeping above the canopy. Farther off, a herd of ceratopsians grinds through ferns, each step a deep, muted thud. This tiny camp, this first experiment in shared space and shared memory, exists in a world of scale we can barely imagine, set against giants that still dominate the landscape, yet already hinting at an intelligence that may one day reshape the fate of an entire era. Yet for all that surrounding power, the most dangerous force in this clearing is not tooth or horn. It is something the troodontids have only just begun to notice: fire. In the late Cretaceous, flame is not rare. It falls from the sky with lightning that spears dry conifer crowns. It seeps up from volcanic vents along rifting continents. It flares where dense mats of fallen needles and fern fronds bake under a relentless sun, until a single spark turns them into a sheet of heat and light. When we step back hundreds of millions of years in our minds, we do not find a quiet, unburned forest. We find an ancient world where smoke columns regularly stain the horizon. Other dinosaurs flee these blazes on instinct. Herds stampede. Pterosaurs wheel away from rising hot air. But the troodontids have something different. Time to watch and brains wired to ask, in their own way, what is this? Their large, forward-facing eyes can track the edge of a fire front from the safety of a rocky outcrop. Their acute hearing catches the crackle. Their sensitive noses register the sharp tang of char. At first, fear rules. Then curiosity edges in. Have you ever seen a crow sidle closer to a campfire, testing how near it can approach? Here, a similar experiment plays out, tens of millions of years earlier. Anatomy both hinders and helps. These are feathered predators with insulating plumage that can ignite in an instant. A misjudged step, a gust of wind, and a curious juvenile could be lost in seconds. Yet that same light, agile body allows quick retreats. Long legs can skirt the margins of a low-intensity ground fire, weaving between smoking logs as insects and small mammals flee in panic. Already we can imagine troodontids learning that if they shadow the flame line, prey comes to them. From this, other uses follow. A smoldering branch dropped by a collapsing tree might be nudged with a sickle claw, then guarded as it glows through the night. A ring of embers at the edge of a sleeping hollow could discourage prowling dromaeosaurs, just as later human fires would keep wolves at bay. On cooler nights in this humid but seasonally variable era, clusters of troodontids might gather near residual heat, extending their activity and social time beyond daylight. Cooking is not a single discovery, but a gradual realization. Scorched carrion is easier to tear. Seeds roasted in ash crack more readily. Tough plant tissues soften and release more calories. Each small advantage feeds bigger brains. Join us as we imagine the moment these feathered hunters shift from merely following fires to tending them, using deliberate burns to clear underbrush or to open paths through cycads and ferns. If a dinosaur can wield flame and begin to set the stage for reshaping ecosystems, what happens when the sky itself turns to fire, an asteroid strikes, and the world starts burning without their consent? When the sky has finished burning and the ash begins to settle, an intelligent troodontid species still has to sleep somewhere. Shelter is no longer just a scraped hollow in the ground. It becomes a blueprint for survival in a world of giants, fire, and shifting climates. What does a city look like when it is designed by a small feathered predator that refuses to live under the feet of the biggest creatures to ever walk the earth? To answer that, we step back hundreds of millions of years in imagination and follow rivers, coastlines, and forest margins. Dense troodontid populations would not choose the open plains where colossal hadrosaurs and titanosaurs graze. They would cluster instead along forest edges, cliff-lined coasts, and braided river valleys, places where vertical structure concentrates food, shelter, and escape routes. The meeting points between habitats set the stage for trade, for nesting, and for the complex social lives that higher intelligence demands. In these zones, their cities rise not outward, but upward. Picture multi-level settlements threaded through conifer trunks and cycad groves and drilled into soft coastal cliffs. Individual nests cling to branches and ledges, while storage niches pepper the rock like swallows' holes, each packed with dried meat, seeds, or carefully cached tools. Between them run ramps of woven branches, natural boughs bent and fixed into living bridges, and carved stair-like ledges that only a sure-footed climber could trust. Their anatomy makes this three-dimensional world natural. A troodontid is light, balanced by a stiff tail, with grasping hands and sickle claws that can hook bark and stone. Where human cities spread in flat grids, their settlements stack and interlock, minimizing ground-level exposure where a single sweep of a sauropod limb or the charge of a massive tyrannosaur could destroy everything. Streets become vertical corridors. Plazas become widened platforms halfway up a cliff face, safe balconies suspended above the traffic of herbivorous giants below. Materials reflect both their limitations and their ingenuity. Early structures might be lattices of woven branches plastered with hardened mud, sun-baked into rigid shells that hug tree trunks and rock walls. Softer rock layers along rivers and coasts could be carved into chambers, their ceilings reinforced with timber ribs. In volcanically active regions, they might learn to quarry denser lava flows, stacking blocks of basalt or andesite into communal halls that resist flood, wind, and the tremors of distant impacts. From above, these cities would not resemble our rectilinear skylines. They would look like extensions of the landscape itself, organic, branching patterns that follow every contour of ridge and ravine. Ribbons of habitation trace river meanders, climb sea cliffs, and spiral up ancient conifers. At night, points of light reveal their presence, the steady, contained glow of controlled fires in cliff chambers, and perhaps in wetter forests, trails marked by cultivated bioluminescent fungi or algae. This is a world of scale we can barely imagine, where even light is pulled into 3 dimensions. Join us as we move from the shapes of their cities to the minds that planned them. How does a creature that lives in such layered space think about maps, memory, and territory? And what happens when that vertical vision turns toward the sky itself? Those vertical cities do not float in a vacuum. Every glowing terrace, every woven bridge of bone and branch must be paid for in energy, in meat and leaf and heat, drawn from an ancient Earth still ruled by giants. When we step back hundreds of millions of years in our imagination, the energy landscape around these intelligent troodontids is staggering. Vast herds of hadrosaurs and ceratopsians move like living continents, colossal reservoirs of biomass locked in armor, muscle, and bone. Between them flow smaller streams of life, scurrying mammals, lizards, and other small dinosaurs, dense stands of ferns, conifers, and early flowering plants, and, along coasts and rivers, shoals of fish and marine reptiles that turn sunlight and plankton into flesh. This is a world of scale we can barely imagine, and yet our troodontids must learn to read it as clearly as we read a map. At first, their survival rests on precision rather than power. They cannot bring down the biggest creatures to ever walk the earth, but they can think around them. Cooperative hunting parties focus on juveniles at the edge of the herds, where a single misstep or moment of panic can separate a young hadrosaur from its colossal guardians. Systematic egg harvesting becomes an art. Night raids on nesting grounds, timed to the breeding cycles of different species, with cached eggs feeding whole communities through lean periods. Managed scavenging follows in the wake of tyrannosaur kills, with troodontids arriving not by chance, but by prediction, tracking scent, vultures, and the habitual paths of apex predators. As their minds and societies grow, subsistence begins to blur into management. Some clans start tending patches of favored plants near their cliff dwellings, clearing shade, dropping nutrient-rich scraps, even carrying seeds from distant valleys. Over generations, they selectively protect certain shrubs and cycads that fruit reliably, while ignoring or uprooting competitors. Elsewhere, they learn to farm the giants themselves, guiding herds with controlled fires, noise, and carefully placed scent markers so that grazing paths repeatedly cross the same floodplains. The herds renew the grass-like understory, fertilize the soil, and leave predictable trails of trampled vegetation, shed skin, and the occasional carcass. In this way, proto-agriculture is not fields and fences, but the choreography of movement across entire valleys. Living among giants brings constant risk alongside this opportunity. A single stampede can erase a settlement, crush storehouses, and wipe out carefully tended plant groves in a thunder of feet and dust. Learning to read herd moods, to hear the first low rumbles of alarm, becomes as vital as tool use itself. Troodontid scouts station themselves on high ridges, mapping the seasonal migrations of sauropods, hadrosaurs, and predators alike, turning what could be random catastrophe into patterned, almost calendrical change. In mastering these flows of meat, plant, and motion, they are already energy managers on a continental scale. The next question is inevitable. Once they understand the living currents, do they begin to see the deeper ones? Wind funneling through canyons, rivers dropping from uplands, steam rising from volcanic springs, and dare to tap those invisible giants as well? To feel what that daring looks like, we need to leave the sweeping plains and drop into the shadows. Follow us down to a clearing at the base of colossal trees, where roots rise like walls and the air is thick with scent and sound. Here, as light filters in broken shafts, a different kind of giant stands out. Not in body, but in mind. Dozens of troodontids from distant valleys and ridges converge in a living marketplace, their feathers catching the sun in flashes of iridescent green and rust. This is not a hunt. This is an exchange. Along one root buttress, toolmakers have laid out their work on a strip of smoothed bark. Carefully flaked stones, each no larger than a human hand, form neat rows. Narrow blades for slicing, squat scrapers for hide, pointed cores that can be struck again to release fresh edges. The shapes repeat from stall to stall. There is already a preferred curve to a cutting edge, a standard thickness that signals reliability at a glance. Near them, foragers step forward in turn, placing rare objects on a bare patch of soil. Clusters of hard, oil-rich seeds from a distant floodplain. Thick-shelled mollusks pried from coastal shallows. A spray of vivid berries from a shrub that fruits only once each season. Each item is angled just so, rotated to expose color, texture, or scent glands, the arrangement itself a kind of language. Negotiation is almost entirely nonverbal at first. Bodies lean in, then away. Tail feathers flare or flatten. Throat sacs pulse with low, steady notes, overlaid with quick chirps that mark interest or doubt. A troodontid assessing a blade tilts its head, then slowly lowers its neck, exposing the side in a gesture of cautious trust, while the seller mirrors the motion, claws held wide to show they are empty. Between these clusters, other specialists move with practiced ease. Storytellers, or perhaps we should call them newsbearers, travel from group to group, their vocalizations more elaborate, their gestures sweeping toward the horizon. They reenact the fall of a cliff face that buried a nesting ground, the arrival of strange scents on the wind, the path of a migratory herd of hadrosaurs. Around them, listeners hold small carved tokens marked with repeated notches and spirals, subtle signatures of distant clans and quality. If we step back for a moment, we recognize the pattern. Trade, specialization, shared signals, and early standardization emerge in many intelligent social species on Earth, from our own ancient marketplaces to the chemical exchanges of ants. Join us as we use this imagined clearing not as fantasy, but as a lens to ask a larger question. Once such networks take root, how far could troodontid civilization spread across this ancient world of scale we can barely imagine? From that trading ground of scents and signals, our imagined troodontids lift their gaze. Networks on the forest floor are only the beginning. To truly master their ancient world, any technological civilization must do something more abstract, more radical. It must start to measure. Before machines, before metal, before cities, there is counting. Not just vague impressions of more or less, but exact amounts, stable patterns, relationships that hold whether you are weighing a carcass or timing a migration. Join us as we follow these feathered thinkers through the first quiet revolution of number, geometry, and time. A troodontid hand is not a human hand, but it is precise. 3 main fingers, a sickle claw on the foot, a jaw that can hold pebbles. We can imagine them marking prey calls with soft clicks, lining up stones along a log, or scratching notches into bark to track how many hatchlings return to the nest. If they count claws on a forelimb, a base 3 or base 6 system might emerge. If they tally individuals in a hunting band, perhaps base 5 or base 10, arises from repeated group sizes. The structure of their bodies and their social habits would quietly set the stage for the mathematics of an entire era. Once quantities are stable, space follows. A stalking predator already understands angles and distances with its body. Turning that instinct into geometry is a smaller leap than it seems. Triangles of trails between nest, water, and hunting ground become mental diagrams. The arc of a thrown stone or dropped bone hints at curves. Over generations, these impressions could crystallize into rules. How far, how steep, how wide? Geometry would not begin on a blackboard, but in the forest, mapping routes through a world of scale we can barely imagine. Above them, the Cretaceous night is almost unimaginably dark and clear. No cities, no smoke from factories, only volcanic hazes and the soft glow of distant lightning. The Milky Way arches overhead as a bright, fractured river of light. Troodontids, likely nocturnal or crepuscular, have large forward-facing eyes tuned to low light. For them, the stars are not faint decorations. They are sharp, insistent points, impossible to ignore. Over many seasons, patterns emerge. Certain star clusters rise when the great herds move north. A bright red star hangs low when particular ferns release spores. The slow drift of constellations across the horizon marks longer cycles, guiding when to lay eggs or abandon a nesting ground. Do they give these stellar patterns names tied to the biggest creatures to ever walk the Earth, or to their own ancestral hunters? Irregular visitors would be even more striking. Comets would blaze as ghostly, moving scars across the sky. Meteor showers would slice briefly through the darkness, leaving troodontids chattering in alarm or awe. With counting and geometry already in place, some minds might start to track these wanderers, to predict their return, to ask what lies beyond the familiar dome of stars. And if they become true sky watchers and pattern seekers, one final question looms over this ancient Earth. Could such a civilization, rooted in number and starlight, one day see the subtle warning signs of the colossal asteroid that will end their age, and try to change the story of extinction itself? To answer that, we have to let the sky itself become a character, not just a backdrop, but a warning. When we step back hundreds of millions of years and replay the final moments of the Cretaceous, we know something the troodontids do not. A roughly 10-kilometer wide asteroid is on a collision course with Earth, racing toward what will become the Chicxulub crater on the Yucatan margin. From our scientific vantage point, we can trace the chain of events. A massive body slams into the planet at tens of thousands of kilometers per hour, vaporizing rock, excavating a crater more than 150 kilometers across, and hurling incandescent debris around the globe. Shockwaves circle the planet. Wildfires ignite as superheated ejecta rains down. Dust, sulfur, and soot surge into the upper atmosphere, forming a shroud that dims sunlight, cools the surface, and unravels food webs in a matter of months. It is an extinction engine written in stone. But imagine this same event through troodontid eyes. In this alternate timeline, their civilization is young yet observant, clustered in coastal forests and river valleys beneath the silhouettes of the biggest creatures to ever walk the Earth. They already track the motions of bright wanderers in the night, mark eclipses, and tie seasons to star patterns. Join us as we stand among them on a warm Cretaceous night as the first anomalies appear. A new star brightens slowly against the familiar constellations. Meteor showers grow more frequent, thin streaks of light whispering across the sky. Careful sky watchers notice that one object does not drift like the others. Its path against the stars is strange, its timing out of step with the cycles they have charted for generations. Is it a messenger or an intruder? Within their gatherings, stories and hypotheses collide. Priests of ancient sky myths declare that a celestial hunter has loosed a burning spear toward the world. Early natural philosophers argue for a different vision. Perhaps this is a wandering stone, a colossal body sharing the heavens with their own planet, now slipping into a deadly resonance. Debates flare around firelight as clay tablets, carved bones, or etched bark record orbital patterns, predictions, and warnings. Then the world itself begins to change. Midday light turns oddly yellow as if filtered through smoke. Shadows lengthen and blur. Even in this lush greenhouse era, some mornings feel unexpectedly cool. Dew lingering on fronds that once dried in minutes. Far away, low rumbles travel through the ground, the distant drumbeat of increased impacts as smaller fragments arrive ahead of the main body. Nights grow restless. Animals call at strange hours. The air carries a faint metallic tang after each meteor storm. Troodontid observatories, stone circles, timber sightlines, or carved cliff markers record the intruder swelling, night after night, from star to point, from point to tiny disk. And then, one day, the sky tears. A blinding streak rips across the atmosphere, turning noon into searing white. Shockwaves race outward. In that instant, with a star falling and oceans about to rise, we are left with one final question. Will all their intelligence, all their fragile understanding of this ancient world, matter at all in the face of a planetary catastrophe? In the breath that follows that blinding flash, the age of giants begins to die. Not slowly, not gently. In minutes, shockwaves roar across continents, flattening forests that had stood for millions of years. Trees snap like matchsticks. Herds of colossal herbivores are hurled to the ground. Tsunamis, higher than coastal cliffs, tear into shorelines, grinding entire ecosystems into churning slurry. We step back hundreds of millions of years in our imagination, yet the violence feels immediate, almost unbearable. Then comes the fire. Superheated debris rains from the sky, igniting global wildfires. Night falls at noon beneath a red, flickering canopy of smoke. For troodontids, even the most advanced, this is not an abstract extinction event. It is burning air, falling ash, and the sudden silence of familiar calls that never answer. In the weeks and months that follow, a different killer arrives. Dust and aerosols spread around the Earth, plunging the planet into a long twilight. Photosynthesis crashes, temperatures fall. A nuclear winter grips the ancient world, turning lush Cretaceous landscapes into cold, dim silhouettes. How could any civilization, no matter how clever, endure a world of scale we can barely imagine in its destruction? Here, troodontid advantages might finally matter. They are not the biggest creatures to ever walk the Earth. They are small, lightly built, with bodies that demand far less food than the massive sauropods and giant theropods around them. Many may already use burrows, dense undergrowth, or natural caves as shelter from predators and climate. Flexible, omnivorous diets allow them to eat insects, small vertebrates, eggs, carrion, even seeds and roots when hunting fails. If some troodontid groups have reached human-level intelligence by this late Cretaceous moment, their response could be organized, not random. Join us as we picture emergency councils in dim forest hollows, individuals calling others back from exposed nesting grounds, herds redirected toward ravines and limestone caverns. Stored food, dried meat, cached seeds, carefully hidden eggs, suddenly becomes the thin line between survival and oblivion. Hunting strategies would change almost overnight. As large dinosaurs weaken or die, scavenging might replace active pursuit, fishing in turbid rivers, trapping burrowing mammals, harvesting insect swarms around carcasses. Every niche becomes an opportunity. Social coordination, already essential for sharing knowledge and raising young, now underpins rationing, patrols, and the defense of scarce shelter. Even so, most would perish. Populations would crash through a brutal bottleneck. Yet a bottleneck does not have to erase culture if communication endures. Small scattered communities, still exchanging signals across valleys or along river corridors, could carry forward stories of the bright star, the burning sky, and the long cold. In that sense, an intelligent, adaptable troodontid lineage might stand a better chance than many colossal neighbors. They could not stop the impact, but they might, just barely, learn how to live in its shadow, and that possibility sets the stage for an entirely different post-extinction Earth. But to feel what that different Earth might have been like, we need to leave the abstract behind. We need to step into the cold. Months after the impact, the great Cretaceous forests are almost unrecognizable. Ash drifts from a dim, clouded sky like dirty snow, settling on blackened ferns and splintered trunks. Between the trees, the ribs of once colossal neighbors arch from the soot. A fallen hadrosaur here, a shattered tyrannosaur there, their bones half buried, their age of dominance ended in a single terrible season. In this frozen twilight, a faint glow leaks from a crevice in a low cliff. Inside, a small troodontid group has gathered around something that, for their kind, is nearly as strange as the impact itself. A carefully shielded ember, coaxed into a fragile fire. The flames are tiny, no bigger than a nest, banked with damp earth and stones to hide the light and stretch the heat. Yet in a world that has suddenly turned cold, this is a massive achievement. Feathers puffed against the chill, they share strips of roasted meat and half-charred seeds, passing food from clawed hands to narrow waiting snouts. Their shelter is rough but deliberate. Woven branches, dragged fronds, and slabs of bark wedged to block the wind. You can almost hear their soft chirrs and clicks echo against the stone as they press closer, turning their sides to the warmth in a ritual of survival. At the back of the chamber, an older survivor shifts forward. One eye is clouded from an old wound, but the other gleams in the firelight, large and forward-facing, reflecting every flicker. With slow, deliberate movements, this elder taps a claw against the wall, tracing fresh lines over older, fainter marks. Circles, jagged streaks, a long curve of land under a spray of downward cuts. Then the performance begins. A rising whistle, a sudden, harsh screech, forelimbs flung upward to mimic the blinding descent. The elder drops flat, body trembling, tail lashing to show the shock that raced through the ground. Dust dances in the firelight as younger troodontids flinch, then lean in. We watch as shared trauma is translated into pattern. Sound, gesture, and symbol layered together until the day the sky fell becomes more than memory. It becomes story. Juveniles cluster near the front, eyes wide, pupils dilated in the gloom. In those eyes, the flames double and triple like tiny suns that did not die. They are not only absorbing fear, they are learning where to run when the ground shakes, how the air smells before the ash begins, which valleys flood, and which ridges shelter life. Practical lessons fuse with a first fragile cosmology. The bright star above, the burning sky, the long cold that follows. Join us as we pull back from this single cave to the wider landscape. Across this battered continent, other pockets of survivors are doing something similar. In their own ways, they are turning disaster into narrative, randomness into pattern. And that act, repeated across eras and species, is one of the quiet hallmarks of cultures that endure. When we compare these imagined scenes to the stories humans tell about floods, fires, and falling stars, we glimpse a world of scale we can barely imagine. What happens if such storytelling troodontids do not vanish with the ash, but carry these myths forward into a new age of evolution? Those myths do not end with the firestorm. They become the first stories told in a colder, emptier dawn. In the Paleogene, the ancient world wakes to a transformed Earth. The colossal, long-necked herbivores and the biggest creatures to ever walk the Earth are gone. No more sauropod silhouettes against red Cretaceous skies. Instead, ash-darkened clouds thin to reveal cooler air, patchy forests, and landscapes where ferns, hardy conifers, and the first expanding carpets of flowering plants reclaim ground. This is not yet a frozen planet, but the stable, greenhouse warmth of the Mesozoic era has fractured. Winters bite harder, food is seasonal, the age of obvious giants is over, and a new contest for survival begins among the small. Into this reset world step three main lineages: early placental mammals, rapidly diversifying modern birds, and our surviving troodontids. They now move through thickets of low shrubs instead of towering cycads, hunting among roots and leaf litter. Mammals, mostly rodent-sized, compete for insects, seeds, and fallen fruit. Birds probe bark, skim water, and scavenge carcasses. Troodontids, already equipped with keen vision and grasping hands, find themselves in direct overlap with both. They stalk the same beetles as shrew-like mammals, raid the same nests as crows' distant ancestors, and eye the same berries that small omnivores depend on. Diet becomes a battleground. So does time. Many mammals favor the night, nursing young in burrows. Birds dominate the open day, flashing between trees. Troodontids, with their large, forward-facing eyes and flexible behavior, can exploit dusk and dawn. But they also have something more: cultural memory. Where mammals rely on rapid reproduction and birds on flight, troodontids can pass down learned strategies, tools, and safe routes, generation after generation. To survive harsher winters and patchier food, these dinosaurs shift. Some lineages miniaturize further, no bigger than modern crows, slipping into dense undergrowth. Others diversify, spreading from forest edges to rocky coasts and floodplains. Omnivory becomes the rule, rather than the exception. A single band might dig for roots, set simple stone wedges to crack seeds, and coordinate hunts for small vertebrates. Shelters change too. Scrapes in the soil deepen into semi-permanent dens, roofed with branches and mud. Over time, these become constructed environments: windbreak walls, communal nesting chambers, even simple storage pits for dried meat and cached nuts. Here, cultural knowledge starts to set the stage for something unprecedented. Fire, once a terrifying force in their stories, is gradually tamed. At first, they steal embers from lightning-struck trees, carrying them in bark bundles back to sheltered hollows. Later, they learn to strike stone on stone, to keep coals alive through the leanest months. With controlled fire, they can roast tough seeds, smoke meat, and warm fragile eggs, pushing their range into colder latitudes that mammals without tools reach only slowly. Proto-agriculture follows in small, careful steps. Troodontid groups learn that disturbed soil near their camps sprouts denser patches of favored plants. Seeds are dropped deliberately along paths. Simple irrigation furrows divert streamlets toward berry thickets. This is not yet farming as we know it, but it is landscape engineering, and it ripples through ecosystems. Where a mammal must wait for evolution to reshape its teeth or gut, a troodontid can reshape its valley within a few generations of shared practice. Join us as we imagine these feathered toolmakers spreading across continents. On coastal plains, they build fish-drying racks and stone breakwaters. In upland forests, they terrace slopes to trap soil and moisture. Each innovation opens a niche that would otherwise be closed, or at least fiercely contested. Birds may still own the open sky, and mammals may still excel in deep burrows and extreme cold, but troodontids begin to dominate the in-between spaces. River corridors, forest margins, and rich floodplains where resources are diverse and predictable. In such a world of scale we can barely imagine, intelligence itself becomes a geological force. The question is no longer whether troodontids can survive the extinction, but what their success means for everything else. If one dinosaur lineage starts to monopolize the most productive habitats through culture, tools, and fire, do mammals remain forever in the shadows, confined to the margins of this new era? Or will some mammalian rivals, perhaps early primates, still find a path to their own macro-intelligence under troodontid dominion? As we follow this alternate Paleogene forward, we have to ask a final, unsettling question. In the long run, does Earth belong to fur, to feathers, or to the minds that learn fastest, regardless of the bodies they inhabit? In this alternate future, Earth does not wait for fur or feathers to claim it. Minds do. Minds wrapped in lean, feathered bodies with sickle claws and night-keen eyes. As the shock of the extinction fades, a new experiment in intelligence steps forward onto a wounded planet. Following the chaos of the KPG, the Paleocene and early Eocene warm the world again. Forests surge back in colossal waves, cloaking continents in dense, humid canopies. For troodontids already adept at climbing and leaping, this greenhouse Earth is an open invitation. They establish cliffside colonies above floodplains, stringing woven bridges between trunks, carving chambers into soft rock, using lightweight branches and resin as their first engineered materials. Here, social learning and tool use are not luxuries. They are the difference between surviving flash floods and being swept away. As we move into the cooler Oligocene, global temperatures fall and open habitats spread. This climatic shift does more than thin the forests. It sets the stage for larger, more coordinated troodontid societies. Exposed valleys and plateaus demand long-distance movement and shared infrastructure. Instead of broad stone roads and wheeled carts, we see elevated causeways of interlocked timber and bone, rail-like perches that let them sprint and glide above ground predators and seasonal floods. Vertical shafts and spiral ramps connect burrows, cliff dwellings, and canopy platforms in a three-dimensional web of movement. By the Miocene, when in our timeline, grasslands nurtured mammalian giants, this Earth belongs to a different kind of giant. Sprawling troodontid city regions that climb rather than sprawl, rising in layered terraces along escarpments and canyon walls. Their cities scale upward, not outward. Imagine continent-spanning networks of elevated pathways, hanging transit lines, and arboreal megastructures that braid together forest crowns. Where we would pour concrete, they grow and sculpt living wood. Where we rely on flat streets, they engineer branching rails and perches, tuned to their balance, talons, and tails. This different body plan drives a different technology. Precision claws and flexible feathered arms favor hooks, clamps, and slotted joints over heavy bolts and plates. Lightweight alloys, woven composites, and tension cables dominate, while true wheels remain rare curiosities. Why roll when you can climb, glide, and descend in controlled drops? Vertical transport becomes their specialty. Counterweighted lifts, inclined railways hugging cliffs, wind-driven hoists that turn updrafts into free energy. Around them, domestication reshapes the ancient world. Smaller herbivorous dinosaurs, if any lineages persist in this timeline, are corralled on ledges and terraces as living lawnmowers and fertilizer engines. Large birds, descended from other theropod cousins, become partners in scouting and message carrying, their sharp senses folded into troodontid communication networks. Mammals, still mostly small, are guided into new roles as burrowers that maintain drainage tunnels, scent trackers that patrol for danger, and sources of insulating fur in cooler epochs. Join us as we follow these feathered engineers across tens of millions of years, watching their science peel back layer after layer of Earth's history. Eventually, their telescopes and instruments turn outward. What happens when a civilization born from an extinction no longer fears the sky, but studies it? When the descendants of Cretaceous hunters begin to ask whether other worlds circling distant suns ever birthed minds as tenacious as their own. As their eyes turn from the sky back down to their own planet, another story unfolds beneath troodontid feet. Before rockets, before radio, before written history, every thinking species must learn one brutal lesson: how to control energy, not just to stay warm, but to reshape an entire world. Humanity's path is familiar. We start with simple firewood, then fields of grain that trap sunlight in edible form. We tap rivers with water wheels, dig deep for coal, drill for oil, and finally lace our cities with invisible currents of electricity. Each step multiplies what a single pair of hands can do. Each step tightens our grip on Earth's resources. For troodontids, the first milestone is the same ancient force, fire. In a Cretaceous landscape thick with conifers and ferns, controlled burns would be both a tool and a danger. Picture cliffside communities deliberately setting low, creeping fires to clear undergrowth, flush prey, and encourage new growth in hunting grounds. With feathers to insulate and keen night vision, they could work the cooling ash fields after dark, learning to treat fire not as a terror from the sky, but as a domesticated lightning bolt. From there, biomass follows. Not plowed wheat fields, but managed fern prairies, cycads, and seed-bearing shrubs, harvested and stored in communal caches. Instead of draft animals, they have coordinated packs of their own kind. Instead of barns, they carve chambers into soft rock, using their sickle claws and tools to create insulated storehouses that turn plant matter and dried wood into a reliable energy bank. Water power would come early. Cliffside cities overlook rivers and tidal channels, perfectly placed to notice that moving water can lift, drag, and grind. Join us as we imagine wooden or bone-framed wheels anchored to rock faces, turned by waterfalls plunging from inland plateaus, or by tides surging through narrow inlets. These devices could lift baskets of ore, grind tough plant fibers, or drive simple hammers long before complex metallurgy appears. Mining transforms the story again. Humans descended underground with flexible hands and upright bodies. Troodontids bring different advantages: compact frames, strong hind limbs, and grasping forelimbs adapted for precise work in tight spaces. Narrow, branching tunnels radiating from cliff bases could follow seams of soft coal or iron-rich concretions, with ventilation shafts opening onto ledges. Their acute senses might let them smell oil seeps or notice subtle sheens on coastal rock, hinting at buried hydrocarbons long before drilling rigs exist. Yet this is where their path might diverge from ours. Living in a world of scale we can barely imagine, under the shadow of the biggest creatures to ever walk the earth, troodontids would grow up with an intimate awareness of ecosystems and collapse. Fossil beds, mudstone cliffs, and ash layers already tell them that entire communities can vanish. Would a civilization born from an extinction rush headlong into a coal and oil age, or hesitate at the thought of filling the air with unfamiliar smoke? Alternative revolutions beckon. Volcanic arcs and rift zones offer geothermal heat, literally venting from fractures in the crust. A species at home on steep slopes could sink early shafts into warm rock, channeling hot water into communal baths, incubation chambers, or primitive steam devices. Elevated ridges and coastal bluffs provide constant wind. From these perches, they could suspend sails or vanes, learning to harvest the invisible pressure of moving air centuries before they ever refine a drop of petroleum. Electricity, when it comes, might arise not from coal-fired plants, but from networks of water and wind machines driving generators high above the floodplains. Instead of sprawling, smoke-choked valleys, we might see lattices of towers and cliff-mounted turbines, their silhouettes sharing the skyline with nesting platforms and observatories. And yet, the core question remains. Any industrial civilization, whether mammalian or reptilian, faces the temptation of concentrated fossil energy. Will troodontids repeat our trajectory, warming their planet with buried carbon? Or will their long memory of past climates and mass extinction set the stage for a different choice? As we follow their technological evolution forward, we have to ask, what happens when a species clever enough to foresee environmental change is also disciplined enough to act before it is too late? To see what those choices might mean, we have to leave theory behind and enter their world. Not the wild Cretaceous forests we know from fossils, but a later age when troodontid ingenuity has reshaped the land into something eerily familiar and utterly alien at the same time. Dawn spills into a hazy valley, and the mist is not just morning fog. It is smoke, steam, and dust rising from a lattice of structures that climb the cliffs and span the river below. Elevated walkways weave from trunk to trunk and rock face to rock face, narrow rails and braided roots serving as highways for feathered bodies. Cranes pivot on wooden towers. Pulley systems loop like colossal spider webs, lifting stone blocks, baskets of ore, and bundles of timber as troodontids sprint and balance along beams and branches overhead. This is not a city of streets. It is a city of perches. Long grasping toes lock around rail edges. Sickles tuck safely away as they cling to vertical posts. With every movement, they exploit a three-dimensional landscape that we, bound to flat ground, can only imagine. Join us as we look closer at how an industrial era might unfold for a species built to climb as much as to walk. Along the valley walls, the rock itself has been carved open. Workshops glow from recesses in the cliff, their entrances framed by chiseled ledges where tools are stored in orderly rows. Inside, teams of troodontids cluster around anvils of smoothed basalt. Some refine metals in clay-lined hearths, feeding charcoal and ore with careful, beak-guided precision. Others shape stone gears and counterweights, turning raw blocks into components for complex mechanisms that rattle and click as they test them on the floor. Everywhere we look, we also see the cost of this progress. Hillsides that once held dense conifer forests now stand stripped, stumps marking former giants. The river that carved this valley has been bent and split, forced through channels and wooden sluices to drive water wheels and carry slag away. Plumes of smoke rise from early furnaces, dark streaks against the pale sky, a visible reminder that even in this ancient world, industry leaves a mark. Yet these troodontids have evolved in the shadow of past extinction. Fire breaks cut through the canopy around nesting zones, rings of bare earth and stone that keep industrial flames from racing into feathered communities. Many workers wear layered plant fiber and resin coverings over their plumage when they approach the hottest hearths. Specialized guilds handle the most hazardous tasks, their crests marked with pigments that signal training, rank, and the dangers they routinely face. In one high workshop, away from the noise of forges, a single engineer crouches over a different kind of machine. It is a device of interlocking stone rings and metal pointers, mounted on a swiveling frame that tracks the sky. As the sun clears the ridge, she adjusts a counterweight with a clawed hand, aligning markers etched with constellations, first mapped by her ancestors. Here, industry and astronomy merge. The same mechanical insight that lifts ore from the valley floor now follows celestial bodies with quiet precision, preparing perhaps for choices and journeys that will reach far beyond this hazy troodontid landscape. If their machines can already trace the heavens, what will they do when they learn to harness the full power of their planet and its skies? If their machines can already trace the heavens, the next step is inevitable. At some point, these feathered thinkers will try not just to follow the sky, but to reach it. To leave a planet, any civilization must first learn a few universal rules. Newtonian mechanics, even if they never call it that, must be grasped in practice. That every action has an equal and opposite reaction. That orbits are a balance between falling and moving sideways. That gravity is both a prison and a pathway. Join us as we imagine troodontid scholars, perched on stone terraces, timing the arcs of thrown stones, the plunge of dropped weights, the flight of gliding tools. Over generations, careful observation hardens into equations carved into clay or etched into polished bone. Materials and energy follow. In this ancient world, volcanic glass, dense woods, and early metalworking set the stage for more ambitious designs. They learn which resins resist heat, Which mineral mixtures burn hotter? Which compressed gases give the greatest push? Energy density becomes not an abstract concept, but a felt reality. Which fuels lift a test capsule a little higher? Which mixtures explode too fast? And which burn with a steady, colossal thrust? Their first rockets do not rise from flat coastal plains. They launch from high plateaus and cliffside platforms, carved into the edges of rift valleys and uplifted mountain shoulders. A troodontid body is light, balanced, built for perching, so their launch towers are narrow, vertical forests of stone and latticework, with ledges instead of stairways. Technicians cling to columns and overhangs, adjusting nozzles with clawed hands, checking bindings with quick, precise movements of beak and talon. Why do they go? In a world where extinction once came from the sky, asteroid monitoring is not a luxury. It is a cultural memory turned into policy. Their astronomers already tracking near-Earth objects with uncanny precision will want sentinels in orbit, then engines capable of nudging dangerous bodies aside. Curiosity pushes them further. What minerals lie locked in nearby asteroids? What stories do the upper atmospheres and moons tell about the deep history of Earth and its giants? Inside their spacecraft, physiology shapes every surface. There are no chairs, only rings of padded perches and vertical support poles, allowing bodies to brace in multiple directions during launch. Control panels arc overhead and beneath, covered in levers and touch plates sized for claws, with bite grips and tongue switches for redundant input. Life support systems hold temperatures and humidity in a narrow band that suits their thermoregulation, perhaps with radiant heat panels that mimic the warmth of a Cretaceous sun filtered through forest canopy. This is a world of scale we can barely imagine. Colossal dinosaurs below, delicate satellites above, all linked by reptilian engineers. And if troodontids reach space first, scattering metal constellations around their planet, what happens millions of years later when, on a distant continent, a primate species looks up? Do we inherit a sky already written with their machines? Faint, ancient beacons, whispering that we were never the first to leave Earth? If the sky is already scripted with ancient machines, what chance does a young lineage on the ground really have? To understand whether we would ever emerge in a troodontid-ruled world, we have to compare it with the only timeline we know, our own. After the KPG extinction, when the asteroid ended the age of the non-avian giants, mammals stepped into a world of vacancies. Apex predators were gone, massive herbivores were gone, entire forests and food webs had been shattered. In that quiet, dangerous aftermath, small shrew-like mammals began to spread into niches once held by dinosaurs, growing larger, experimenting with new diets, and eventually giving rise to primates in warm, complex forests. Those primates, with grasping hands and forward-facing eyes, set the stage for big brains, social learning, and much later, our own technological species. Now imagine that extinction never fully cleared the board, because one lineage of dinosaurs not only survived, but rose. Intelligent troodontids, already gifted with keen vision and high brain-to-body ratios, become ecological engineers. They hunt, they plan, they reshape habitats, they burn forests to flush prey, they terrace riverbanks, they fence off rich feeding grounds the way we fence off farms. In such a world, where does a small nocturnal mammal hide long enough to grow bold, diurnal, and large-brained? Predation pressure alone would be immense. Troodontids with tools and coordinated strategies could track burrows, lay traps, and patrol the night with artificial light. Habitat modification would close many of the opportunities that real mammals exploited after the asteroid. Forest gaps, fruiting trees, and insect-rich clearings might be managed resources guarded by dinosaurian overseers. Resource competition becomes asymmetric, one side armed with culture and technology, the other with only instinct. In that scenario, most mammals remain small, secretive, and peripheral. They cling to the shadows of a world of scale we can barely imagine, active at the edges of troodontid activity, feeding on scraps, seeds, and insects. Primates, if they arise at all, may be confined to isolated islands or dense marginal forests, never allowed to radiate into the broad sunlit habitats that in our timeline nurtured larger bodies and expanding brains. Without safe access to abundant, high-quality food and complex social networks, the evolutionary push toward human-level intelligence is blunted before it can begin. Yet evolution rarely stops entirely. Join us as we consider stranger possibilities. Perhaps clever, raccoon-like omnivores learn to raid troodontid refuse heaps, solving problems in the margins of dinosaur cities. Maybe burrowing mammals insulated from direct control develop elaborate underground societies, using touch and sound in place of light. Could an intelligent mole rat analog or a sly mustelid-like scavenger slowly accumulate problem-solving skills, memory, and even simple tool use in the cracks of this controlled Earth? Even then, any rise would occur under watchful eyes. Troodontids, attuned to patterns and threats, might notice when a mammal starts opening containers, avoiding traps, or coordinating raids. Do they domesticate these lineages, turning potential rivals into managed helpers, or suppress them before they become competitors? In either case, humans as we know them are extraordinarily unlikely. If any primates evolve, they do so as minor actors, their evolution forever constrained by dinosaurian superiors who reached the stars first. And if those superiors choose to guide or reshape mammalian evolution, the story of intelligence on this planet bends in an entirely different direction, one we have yet to fully imagine. To imagine that different direction, we have to step inside troodontid minds shaped by the hunt. Before farms, before herds, before the idea that killing is something distant and outsourced, their ethics begin with teeth, claws, and the quiet breath of prey in the dark. Predation for them is not a fall from innocence, it is the fabric of existence. Where human moral systems often grow from agricultural roots, protect the herd, sanctify the field, condemn unnecessary bloodshed, a troodontid philosophy would accept that life is fed by death and that violence is not abolished, but refined. Join us as we explore a world where the most respected thinkers are not those who reject killing, but those who decide with exquisite care when it is justified. As omnivores, these descendants of one of the biggest creatures to ever walk the earth in terms of cognitive potential would see a spectrum, not a divide, between plant and animal food. Crushing a seed, taking a hatchling, cutting down a tree, all are incursions into other lives and territories. Their ethics might demand that each act of consumption be acknowledged through gesture, posture, or song, turning meals into small, solemn rituals that constantly remind them of their place in a chain of taking and being taken. Territory in such a culture is not just land, it is story, ancestry, and obligation. Codes of honor would likely govern how hunts cross boundaries, who may strike first, and when a chase must be abandoned. Intraspecies conflict could be tightly constrained, ritualized combat with claws sheathed or dulled, choreographed displays of feather, stance, and voice designed to resolve disputes without crippling wounds. The deepest taboos may fall not on killing itself, but on wasteful killing, surprise attacks on sleeping kin, or the silent erasure of a rival's lineage. Their art would grow directly from bodies built for display. Feathers become living canvases, rearranged daily into intricate patterns that signal mood, allegiance, and memory. Rock faces along forest edges might bear carved reliefs of trackways, storms, and distant asteroid trails, etched and re-etched across centuries. In shaded clearings, they could perform complex movement displays, weaving through ferns in synchronized spirals while layered vocal performances echo between trunks, mapping invisible structures of rhythm and meaning in the air around them. Living in an ancient world of colossal cycles, Troodontids would sense time on a scale that dwarfs our written history. Fossil beds exposed by erosion, shifting shorelines, and the lingering legend of an earlier impact would set the stage for myths of falling stars, drowned continents, and near extinction. Survival and adaptability become their highest virtues. To change plumage, tactics, or tools as climates and continents move is not betrayal of tradition, but its fulfillment. Yet this raises a final, unsettling question. If such a predatory, reflective culture ever looked across the canopy and found another intelligence rising, a late-blooming primate with fire and fragile hands, would they approach us as rivals to be contained, as clever animals to be curated, or as potential partners in a shared, precarious story? The answer might decide which mind inherits the Earth. To feel what that decision might look like, we shift from speculation to a single, fragile moment. Not in our cities, not in our era, but in a raw landscape where intelligence is still learning what it means to meet itself. Picture a rugged valley at the edge of an ice age, cliffs rising like broken teeth above a river that cuts through stone. A small band of early Homo moves along the water's edge, wrapped in hides, carrying chipped stone blades and a guarded fire that hisses in the wind. They expect predators. They expect cold. They do not expect to look up and see feathered bipeds hanging from the cliff face, slotting pale stone blocks into an elaborate lattice of ledges, ramps, and woven platforms. The Troodontids are smaller than the biggest creatures to ever walk the earth, but in this moment, scale is not about mass. It is about meaning. Their sickle claws grip carved niches. Their hands, longer fingered now after millions of years of evolution, pass tools along living chains of bodies. Ropes of braided plant fibers stretch between anchor points. Smoke drifts from clay-lined vents, where something glows with a steady, contained light. For a long heartbeat, both groups simply watch. The humans cluster around their fire, knuckles whitening around spears. The Troodontids pause on their scaffolds, heads tilting in uncanny synchrony, large forward-facing eyes catching every flicker of movement. We see mutual observation as an experiment. They study our chipped flint edges, the rhythm of our gestures, the way we guard flame as if it were a living thing. We study their cliffside architecture, their coordinated movement, the quiet precision with which they never waste a step. Then the pattern breaks. One Troodontid descends in a series of controlled drops and glides, feathers flaring for balance, until it stands a short distance from the humans. No charge, no obvious threat, only stillness and a soft series of layered clicks and whistles that rise and fall like structured birdsong. A human steps forward, heart pounding, and lays a stone hand axe on the ground between them. Join us as we watch the first objects cross that invisible line. A Troodontid sets down a carved bone tube in return, etched with spirals that echo star paths and seasons remembered across a civilizational memory far older than any human story. Hands mimic hands. Heads tilt in mirrored curiosity. Both sides test vocal sounds, repeating tones, trying to find patterns in an alien throat. Yet beneath these gestures, asymmetries grow. The Troodontids carry an archive of past extinctions, volcanic winters, and shifting seas encoded in myth and record. The humans carry something else: raw adaptability, a restless drive to reshape every valley, every tool, every idea in a single lifetime. Which matters more in a world of scale we can barely imagine? We leave the cliff at dusk, outcome unresolved. Trade may blossom here, or conquest, or quiet withdrawal into separate stories. This ambiguous contact sets the stage for our next question. On an alternate Earth, shared by two rising minds, whose future truly unfolds. To move forward, we have to pause. Before we follow our Troodontid thinkers into cities, starships, or extinction-level choices, we need to ask a grounding question. What do we truly know, and what are we carefully imagining on top of that? From the rocks of the late Cretaceous, the hard data are clear but limited. Troodontids were small, lightly built predators, roughly human-sized in length, but far lighter, living in the final chapter of the Mesozoic era alongside colossal hadrosaurs and tyrannosaurs. Their fossils, scattered across North America and Asia, include delicate skulls with enlarged brain cases, long grasping hands, and crescent sickle claws. CT scans of those skulls allow researchers to reconstruct the shape of the brain cavity, revealing a brain-to-body ratio unusually high for non-avian dinosaurs, edging into the range of modern birds. Forward-facing eyes hint at binocular vision. Ringed bone around the eye suggests sensitivity to low light, perhaps a crepuscular or nocturnal hunter moving between giants. We also have rare but powerful snapshots of behavior. Troodontid nests, ringed arrangements of eggs, sometimes in multiple layers, indicate planned nesting sites rather than scattered laying. The structure of the eggshells and the arrangement of embryos point to brooding or at least attentive guarding. In some formations, repeated nest levels through time suggest site fidelity, a memory of place carried across seasons. These are not blueprints for philosophy, but they are a foundation for complex, socially mediated lives. To imagine what that foundation might support, we turn to their living relatives. Modern birds and reptiles show us that small brains, by human standards, can still unlock remarkable cognition. New Caledonian crows fashion hooked twigs to fish grubs from crevices. Goffin's cockatoos disassemble and reassemble multi-part tools in laboratory tests. Parrots and corvids learn from one another, passing local traditions across generations. Even reptiles, often dismissed as simple, surprise us. Monitor lizards solve mazes. Some turtles learn visual patterns and remember them months later. When we ask whether a troodontid could, over millions of years, reach human-level intelligence, we are not leaping from nothing. We are extending a real, observable spectrum. Yet evolution is not a ladder. It is a branching, contingent process. Intelligence at our level seems rare, not because evolution aims low, but because it is expensive. Large, energy-hungry brains, extended childhood, intricate social structures. All of these require stable resources and very specific ecological pressures. A shifting climate, a stray mutation, a different predator, and the path we are tracing might never appear. Our scenario is plausible in broad strokes, but never inevitable. On another Earth, troodontids remain clever night hunters and nothing more. Throughout this episode, we have stepped beyond the data to picture tools, cities, trade, and timelines. The shapes of troodontid hands, the capacity of their lungs, the limits of reptilian vocal cords. These details of technology and language are informed extrapolations, not predictions. The diplomatic cliffside meeting, the possible space programs, even their strategies for facing the impactor at the end of the Cretaceous period, all live in that speculative space. What anchors us is that the science keeps moving. New troodontid fossils emerge from Mongolian deserts and North American badlands, adding species, growth stages, and sometimes hints of feathers. High-resolution CT scans refine our estimates of brain regions, inner ear balance, and sensory priorities. Studies of bone histology reveal growth rates and maturity patterns, clues to lifespan and parental investment. As these discoveries accumulate, they may tighten or overturn the range of futures we can reasonably imagine for these animals. So, where does that leave us? Standing at a crossroads between rock and possibility. Join us as we take one more step, asking not only what troodontids could have become, but what their story reveals about our own fragile contingent rise on this ancient Earth. If troodontids stood at a crossroads of possibility, they also stood inside a cage of limits. Evolution opens doors, but it also locks many of them. To ask whether they could ever rival us is to ask how far bone, blood, and environment can really be stretched on this ancient Earth. We begin with the engine that powers any big brain: metabolism. Modern birds, the living heirs of small theropods, run on high-octane, warm-blooded systems. Yet even they face strict energy budgets. A massive, human-sized troodontid brain would demand a constant flood of calories and oxygen, and it would generate heat that must be shed efficiently. Mammals evolved dense networks of scalp vessels and sinuses to cool our brains. Theropods relied on different skull plumbing and air sacs. Could that system scale up without overheating the very organ driving their intelligence? Or would brain size stall at a clever crow ceiling? Reproduction adds another constraint. Troodontids laid eggs, as far as we can tell, in ground nests. Large-brained animals usually need long childhoods and prolonged parental care, but eggs must be small enough to incubate safely, and hatchlings emerge relatively underdeveloped. For troodontids to reach our level, they might require fewer, larger eggs, thicker shells, and extended brooding, tying parents to the nest and raising the risk that a single drought, predator, or flood could erase years of investment in one storm. That trade-off may have set the stage for intelligence, yet also capped how far it could rise. Lifespan and development are equally critical. Humans spend more than a decade in intense learning before full independence. Did troodontids live long enough for such a drawn-out juvenile phase? Bone histology hints that many small theropods grew quickly and died young compared with us. To support complex culture, they would need to slow down, mature later, and carry knowledge across many seasons. In a world of colossal predators and frequent ecological upheaval, can a lineage afford that kind of patience? Then there is the ceiling imposed by the world around them. Even the biggest creatures to ever walk the earth were ultimately limited by climate, nutrients, and catastrophe. A troodontid civilization would compete not just with mammals and other small theropods, but with giant herbivores reshaping forests, with shifting sea levels drowning coastal plains, with volcanic pulses, and, ultimately, with the specter of extinction from space. How complex can any culture become when entire continents can be reset in a geological heartbeat? Finally, anatomy itself may have been a bottleneck. Their hands were flexible, but not primate hands. Their sickle claws were built for gripping prey, not threading needles. Their vocal tracts, more bird-like than mammalian, might favor whistles and complex calls, yet perhaps not the same dense consonant-vowel chains that our languages exploit. Even with tools, fire, and writing, their technology might have followed different paths, excelling at some tasks while never quite reaching others we take for granted. Taken together, these constraints remind us that human-level intelligence is not an inevitable summit. Yet, they do not erase troodontids from contention. Within those limits, they could still have become one of the most cognitively sophisticated lineages this planet has ever seen, crafting a different kind of mind under the same ancient sun. Join us as we now imagine what such a mind might build, if given time, stability, and a world of scale we can barely imagine. But that imagined troodontid mind never had its chance. To understand why, we have to return to the real end of the Age of Giants, to the moment when the Mesozoic era closed in a burst of fire and darkness. 66 million years ago, a massive asteroid, roughly 10 kilometers across, slammed into what is now the Yucatan Peninsula. In an instant, rock vaporized, shockwaves raced around the globe, and tsunamis tore across ancient coastlines. This was not an isolated catastrophe. Around the same time, colossal volcanic eruptions in the Deccan Traps flooded parts of India with lava, releasing pulses of carbon dioxide and sulfur gases. The climate lurched. First came intense heating, then a plunge into cold as dust and aerosols dimmed the sun. The impact winter strangled the base of the food web. Plants withered. Plankton in the oceans collapsed. When the primary producers fall, everything above them trembles. Large herbivores starved, and with them the giant predators that depended on their biomass. Even agile, sharp-eyed troodontids hunting under darkened skies faced a world where each successful kill was followed by longer and longer stretches of nothing. In that fragile interval, survival hinged on chance as much as on design. Where you lived, what you ate, how big you were, whether you could shelter or burrow or wait out months of scarcity, all of these mattered. But so did sheer luck. A nest laid a little farther from the blast hemisphere. A lineage already adapted to seeds, carrion, or detritus. Small generalist mammals hiding in burrows and hollow logs, and small feathered dinosaurs that would become birds, slipped through the evolutionary bottleneck that closed around the biggest creatures to ever walk the earth. This is the deep contingency that set the stage for us. Without that asteroid, without that particular sequence of eruptions and climate swings, mammals might have remained minor nocturnal players beneath reptilian giants. Our own rise and the absence of a troodontid civilization are two sides of the same cosmic coin toss. How many near misses in Earth's history reshaped the entire trajectory of evolution without leaving a trace we can see? Join us as we now turn that lesson back on ourselves. Intelligence can read the skies, model climate, and deflect at least some threats. It can also build nuclear arsenals, destabilize ecosystems, and amplify vulnerability on a planetary scale. We are both our own best defense and our most dangerous asteroid. The dinosaurs remind us that dominance is not insurance. Lineages that spanned continents vanished, while tiny, adaptable survivors diversified into new forms, from songbirds to primates. In the far future, if another mind studies the rocks and wonders about us, will they craft speculative documentaries about a vanished human world, the way we imagine an unrealized age of Troodon? Or will the story take an even stranger turn than we can foresee? To answer that, we need to split the story in two. Not by changing the laws of nature, but by changing who rises to read them. Imagine for a moment two Earths hanging in the dark, side by side, each turning through the same ancient night. On the left, our familiar planet. Forests echo with the calls of early mammals, then with the voices of hominins learning to shape stone. On the right, an alternate world where troodontids survive the extinction and diversify, their keen eyes and large brains carrying them into a new era. The continents drift in the same directions. Volcanoes roar with the same force. Gravity presses down with the same relentless pull. We move in closer. On one Earth, a human ancestor cups a flickering flame, the first controlled fire staining cave walls with smoke. On the other, a ring of feathered troodontids huddles around a carefully tended blaze, sickle claws feeding resinous branches into the embers. Different hands, different posture, but the same chemical reaction, the same leap from darkness into light. Time accelerates. Symbols appear. On our side, ochre marks and carved bones slowly become writing on clay tablets. On theirs, claw tips and flexible fingers incise spirals and angular characters into damp mud, perhaps accompanied by whistles and hisses shaped by an evolved vocal apparatus. Both civilizations learned to trap spoken language in durable form, and with it, to speak across generations. Cities rise. Human skylines grow from mud brick to stone to steel, towers thrusting vertically. Troodontid cities sprawl more horizontally, adapted to light, hollow-boned frames and tails that demand space to balance. Their architecture favors sweeping ramps, latticework platforms, and sheltered canopies that echo the forest understory where their ancestors hunted. Industrial smoke climbs from both worlds, but in different patterns. Here from clustered chimneys, there from elongated low-lying complexes built to fit a horizontal body plan. We watch rivers change color, forests retreat, and coastlines bristle with harbors on both Earths. The environmental impact is unmistakable. Yet the details diverge. Perhaps troodontid industries lean more heavily on chemical synthesis than on massive mechanical leverage. their fine motor skills and sharp senses, pushing them toward intricate devices rather than colossal machines. Do they burn as much fossil carbon, or do they exploit thermal vents and sunlight with equal intensity? The atmosphere responds according to the same physics, regardless of who lit the first furnace. Now both screens show launch pads. On our Earth, a rocket shudders and rises, a pillar of fire lifting human instruments beyond the sky. On the troodontid Earth, a sleeker vehicle arcs upward, its controls designed for three-fingered hands and wide, forward-facing eyes. The chemistry of fuel and the equations of orbital mechanics are identical. Only the silhouettes inside the capsules differ. Join us as we hold these mirrored worlds in view. In both, evolution has produced minds that can model atoms and galaxies, that can imagine their own beginnings and endings. Intelligence in this light is not a human property, but a way the universe becomes aware of itself. Two Earths, two lineages, one underlying reality. And yet, if we shift our gaze again, what other paths might that same reality allow? If we follow that question to its source, we arrive at a single, slender dinosaur standing in the Cretaceous twilight, Troodon. Not the biggest creatures to ever walk the Earth, not a colossal predator or armored giant, but a lightly built, sharp-eyed hunter with a brain that seems too large for its body. In a world of massive muscles and bone, Troodon represents something quieter, the possibility of mind. Across the last few decades, Troodon has taken on a special role in our stories. Documentaries linger on its large forward-facing eyes and unusually high brain-to-body ratio. Speculative art gives it tools, campsites, even star maps. Science fiction imagines cities of feathered beings descended from troodontids, launching rockets while sauropod herds still roam below. When paleontologist Dale Russell proposed his famous Dinosauroid based on Troodon, he did more than sketch a model. He set the stage for an entire branch of prehistoric imagination. Why does this particular dinosaur captivate us so deeply? Part of the answer lies in the idea of a near-miss intelligence. We are drawn to species that almost, but not quite, crossed the same cognitive threshold we did. Chimpanzees that learn signs, crows that bend wires into hooks, octopuses that solve puzzles in the dark. Troodon joins this gallery as an ancient counterpart, a reminder that the spark of complex thought may have flickered long before our lineage appeared. It invites a haunting question. How many times has intelligence nearly taken off on this planet, only to be cut short by extinction or chance? When we imagine troodontids refining tools, teaching their young, or planning hunts together, we are really probing a deeper issue in evolution. Is a mind like ours a rare accident, balanced on a knife edge of improbable events? Or is it a common outcome once brains reach a certain scale and social lives become intricate? Join us as we consider Troodon not just as a creature, but as a test case. If intelligence evolved once among mammals and once among birds' dinosaurian cousins, might it have blossomed independently in troodontids given a few tens of millions more years? Thought experiments like this may seem speculative, yet they sharpen our understanding of how evolution and cognition intertwine. By asking what an intelligent Troodon civilization might have needed: more flexible hands, richer communication, stable social groups, we clarify which traits in our own story were essential and which were contingent. We also confront how fragile our position is. A slightly different asteroid path, a slightly different climate, and perhaps we would be the near miss, remembered only in someone else's fossils. In that sense, Troodon becomes a mirror. Through its imagined eyes, we see our cities, our tools, even our anxieties, as just one expression of a broader evolutionary possibility. As we step back hundreds of millions of years in our minds and then return to the present, we are left with a final challenge. What does it truly mean that, for this brief moment, it is our species, rather than a feathered reptile from the Cretaceous, that tells the story of Earth. In our closing chapter, we will bring these threads together, measuring what this hypothetical Troodon legacy reveals about our own and about the future paths intelligence on this planet might yet take. So where does this leave us? Here at the edge of two histories, one real, one imagined. When we step back hundreds of millions of years in our minds, we find that both begin in the same place. A quiet Cretaceous forest under a canopy of ancient conifers and flowering plants, with a small, bright-eyed hunter moving through the dark. In the fossil record, Troodon is no mythic giant. It is a lean, human-sized predator, light-boned, feathered, and built for speed. Forward-facing eyes hint at excellent depth perception in the dim hours of night and twilight. A large brain for its body rivals that of modern birds and some mammals. Delicate hands, a sickle-shaped claw, and evidence of nests and eggs suggest not only agility, but care, planning, and perhaps complex behavior around the next generation. From that modest starting point, we followed a speculative trajectory. What if those hands became more flexible? The wrist and shoulder unlocking a greater range of motion, the fingers refining their grip until tools were no longer just picked up, but shaped with intent? What if the spine straightened, the tail shortened, and the body balanced more upright, freeing the upper limbs for technology? What if the voice box and skull evolved to carry layered vocal sounds, then true language, echoing through Mesozoic nights? Join us as we trace that path further. With language comes shared memory. With shared memory, culture. We imagined troodontids hunting together, teaching, forming alliances, and building early shelters along riverbanks, while colossal herbivores grazed nearby. Over millions of years, stone tools could give way to metals, campfires to managed energy, scattered camps to cities, scaled to a world still ruled by massive reptiles and shifting continents. Along the way, we kept returning to the scientific themes beneath the story. Evolution works with constraints as much as possibilities. Eye placement, hand anatomy, respiratory design, and growth rates all set the stage for what intelligence can become and what it cannot. Contingency rules this era and every era. A slightly different climate, a different predator, a shifted orbit, and Troodon's lineage might vanish before it ever experiments with a sharpened stick. On our alternate Earth, however, it does not vanish. Instead, troodontid civilizations reshape ecosystems, manage forests, perhaps domesticate smaller dinosaurs, and compete directly with mammals for niches. In such a world of scale we can barely imagine, primates may remain in the understory, clever but constrained, never given the open ecological space to rise to the level we now take for granted. And then, the impact. In our scenario, intelligence meets extinction head-on, reading the sky, perhaps diverting disaster or rebuilding afterward. The same bright eyes that once watched insects on a fern frond might one day watch stars from an orbital station, as feathered astronauts become, in time, the biggest creatures to ever walk the Earth in a cultural sense, extending their reach far beyond their home planet. Yet our own planet tells a different story. The real Troodon disappears at the end of the Cretaceous period, leaving only scattered bones and hints of potential. As we close, we return to that Cretaceous forest night. A single Troodon pauses, head tilted, pupils wide. In that small skull lie countless futures, cities that will never rise, constellations that will never be named, questions that will never be asked. What does it mean that those futures ended there while ours continued? In our final section, we will turn that question back on ourselves and ask what responsibilities come with being the lineage that did cross that threshold into self-aware, world-shaping intelligence. We have traced a path from an ancient forest floor to a mind that might have rivaled our own. Now, we want to hand that path to you. Because this is not just a story about fossils and neurons. It is a question about what kind of world you choose to imagine. So first, we would like to ask, which Earth feels more compelling? or more unsettling to you? The one we know, shaped by mammals, primates, and eventually humans? Or the alternate history in which a troodontid lineage survives extinction, refines its already remarkable brain-to-body ratio, and slowly builds cities beneath the shadows of colossal sauropods and tyrannosaurs? When you picture those two timelines side by side, which one pulls at you more and why? In the comments, we invite you to take one specific strand of that troodontid world and make it your own. Choose a single aspect of their lives and describe it as clearly as you can. Perhaps you imagine their art, pigments ground from iron-rich clays, painted in spirals that echo the shape of ammonite shells. Perhaps you hear their music, hollow-boned flutes, and deep, resonant drumming on stretched reptilian hide, echoing across a warm Cretaceous night. Perhaps you see their sports, coordinated pack races through dense conifer forests, or ritualized duels where sickle claws flash but never quite strike. Or you might focus on family structures with shared nests, communal care of eggs, and elders teaching the youngest how to read the stars. When you write these scenes, you are not just reacting to the video. You are helping to set the stage for a world of scale we can barely imagine. A world where the biggest creatures to ever walk the earth live alongside a thinking, tool-making predator that never gave way to us. How would such a civilization remember the asteroid? As a myth? As a near miss they learned to predict? As the central story that defines their ethics and their science? We would also like your help in choosing where we step back hundreds of millions of years next. If you could follow another lineage into an intelligent future, which would you choose? A pack-hunting dromaeosaur with even sharper cooperative instincts? A social hadrosaur that turns its crests into communication towers? An ancient marine reptile that brings technology into the oceans instead of onto land? Tell us which dinosaurs or other extinct species you would like to see explored with this same depth and speculative detail. If this long-form journey through deep time and alternate evolution has resonated with you, your support directly shapes what we can create next. When you like this video, subscribe and share it with someone who loves deep prehistory. You help make space for more careful, research-grounded explorations of paths evolution might have taken. And if you would like to keep traveling, we have linked related episodes on dinosaur intelligence, mass extinctions, and the evolution of the human mind itself. Join us as we follow those threads, and then, in our final section, turn back to a more unsettling question. What will future minds, if they arise, imagine about us? We end not in a laboratory or a simulation, but under a real sky. Above you tonight, the same stars burn that watched Troodon hunt, learn, and watch in the late Cretaceous. Before screens, before cities, before history itself, this quiet darkness was all any mind had. Imagine a lonely floodplain 70 million years ago. The air is warm. The silhouettes of colossal hadrosaurs drift along a riverbank, and a small troodontid pauses in the shadows. Large, forward-facing eyes tilt upward. It is not naming constellations or calculating orbits. Yet somewhere in that enlarged brain, in that ancient world of tooth and feather, a new kind of question may be forming. Now we step back hundreds of millions of years in our imagination, then rush forward again to this moment. A human stands at the edge of a desert, or beside a museum wall lined with massive fossils, or in a dark sky reserve where the Milky Way cuts a bright scar across the night. You look up. In the black between stars, another figure seems to flicker into place. The faint outline of a troodontid ancestor, head raised, gaze aligned with yours. Two very different bodies, one shared direction of attention. Curiosity itself becomes the bridge. Across extinctions, across entire eras, across everything evolution has erased and remade, there is this repeating pattern. Some creature somewhere eventually begins to ask, where did we come from? What else is out there? How long will this last? We often tell our own story as if we are unique, the first and only thinkers to emerge on Earth. Yet Troodon's high brain-to-body ratio, its keen vision, its possible parental care and social behavior, remind us that the potential for complex minds was seeded long before us. The asteroid that ended the age of the non-avian dinosaurs did not end that potential. It redirected it. In another timeline, those bright seeds might have flowered into cities of feathered engineers, observatories run by reptilian astronomers. The first space program launched not by primates, but by descendants of that watchful hunter in the dark. That world of scale we can barely imagine did not happen. Ours did. But the fact that it could have existed tells us something profound about intelligence itself. In any timeline, on any Earth that lasts long enough, some lineage will likely learn to read the sky. The details change. The questions remain. They ask about origins, about futures, about their place among the biggest creatures to ever walk the Earth, and the smallest atoms in their own hands. So when this video ends, if you can, step outside. Let your eyes adjust. Find a single star and hold it in your gaze. Remember that your thoughts in that moment are one branch on a vast branching tree of possibilities. A tree that once included Troodon and may yet include minds we cannot foresee. Join us as we carry that awareness forward. Because in the end, Troodon, humans and every thinking creature are the same kind of phenomenon. Brief, bright sparks in Earth's long, deep history, lighting the darkness just long enough to wonder what it all means.